Welcome to our workshop. We are organizers of ACSMD 2021 workshop. We will begin with the opening keynote from our side. So let me share my screen for that. So yeah. Okay, first of all, so yes, we are organizers of the workshop. My name is Hyuk-Jun Kwon, and other organizers are Professor Chai Krishna at Georgia Tech, and Yangjun Lai from Facebook, and Yushin Chen from Facebook, and I'm also from Facebook. So I think I should minimize this. Okay. So as the opening keynote, so we will present the architecture compiler system co-design opportunities for emerging multi-modal DNN workload as a motivation to all of the topics we cover in the workshop. And so the organizers from Facebook are from on-device AI team in Facebook Reality Labs. So first of all, I think first of all, I think the basic question regarding this topic is what are actually the multi-modal DNN workloads? And there are many types of multi-modal DNN workloads. So for example, the first type is a pipeline DNNs. Let's think of the smart speaker we use. And the smart speaker usually provide the speech-based interaction. And they are often triggered by some keywords such as "Hey Facebook." Then the speaker activate the speech processing model, which actually processes the commands you give to the speaker. And as you can see here, we are using different. We can use different DNN models for the first job, which is keyword spotting, and we use different DNN model for speech processing. So for this pipeline DNNs, they perform back-to-back execution, and they have dependencies between those DNN models. And another type of the multi-modal DNN workload is the concurrent DNNs. And let's think about the example of VR headset. So VR headset can do the eye tracking for forwarded rendering, and for the user safety, so it will detect the obstacles around the user. And it can also include the video processing for enhancing the video quality of the VR headset. And all of them actually run in parallel as a part of different services. So they run in they perform the concurrent execution, and each of them has specific deadline for their own functionality. And the last type we want to highlight is the concurrent and pipeline DNNs, which is a mixture of type 1 and type 2. And let's take a look at the more detailed example of the VR headset. So we will have obstacle detection, and let's assume that the eye tracking and the video processing is somewhat pipelines for forwarded rendering, and we are using another DNN for forwarded rendering. Then we get the dependence chain like those in type 1, but we still need to run parallel the models for obstacle detection and so on. So for this type of multi-DNN workloads, we have challenges from both type 1 and type 2. And these kind of multi-modal DNN workloads are currently everywhere. So from the edge devices or mobile devices, such as smartphone, it runs many services like translation, forward denoising, and so on, which all use DNNs nowadays. And if we increase the scale to a little bit larger, then we can think of the self-driving system, which also has multiple subtasks that uses DNNs. And if we further increase the scale, we can also think of the data centers. It also runs a lot of services such as recommender system, speech recognition, and so on. So the bottom line here is that the DNN using DNN models for each subtask is current trend, and they result in multi-modal DNN workloads, which is the main topic of this workshop. So let's take a further deep dive into an example of the AR glasses. So AR glasses could have many applications such as optics display and audio interaction, computer vision, and system design, and the UX. And many of them today are based on the AI, which uses a lot of different DNN models. And one feature we want to highlight is that those applications are highly heterogeneous. So in this diagram, so we have 4 axes, which are memory bandwidth, computation intensity, usage frequency, and latency sensitivity, which shows the characteristics of each workload for each subtask. So let me begin with the audio application. So audio DNN models usually require a high memory bandwidth, and it involves high computation intensity. But latency-wise, it is less sensitive. And for usage frequency, so because we are not talking to the air glass, we will not talk to the air glasses all the time. So the frequency is expected to be somewhat low. And if we think of the video understanding, the memory bandwidth requirement is also high, and computation intensity is also high. And it is more latency sensitive than the audio because it is related to the reaction time to the users. And usage frequency will be also high because the AR glasses, we will use that to look around many things, and we would want to process those. So usage frequency will be higher than audio. And if you think of the eye tracking application, the memory bandwidth and computation intensity-wise is lower than other DNN models, but it is very latency sensitive because it is directly related to the interaction between your AR glass and the user. And usage frequency-wise, the eye tracking is likely to be always on, so the usage frequency will be also very high. And if we think of the hand tracking, which is a kind of another interaction method between the AR glass and user, the memory bandwidth and computation intensity-wise somewhat in the middle of all of those. But it is also latency sensitive, and usage frequency, it is also quite frequent, but not as frequent as eye tracking because we want interacting with the AR glasses all the time using hand. And the last model in these examples are the keyword spotting. So keyword spotting is something like hey face we saw in one of the previous slides and for the smart speaker example. So for memory bandwidth, computation intensity-wise pretty small, and it is not that latency sensitive. And frequency-wise also, it is not expected to be very frequent. So the bottom line here is that we have many different applications and all rely on the DNN models, and they have very different characteristics, which makes the multi-DNN model actually heterogeneous. So multi-DNN workloads are often coming with the high heterogeneity, as you can see examples here. So such heterogeneity and having multiple model inside the workload imposes a lot of challenges across all the computation stack, from the software, from the model side, way down to the hardware architecture. For the model side, so model need to run in conjunction with other DNN workloads. So now the research question arises if we want to optimize for individual model or if we want to optimize workload holistically. So and many other research questions like this. And for the OS and runtime, so we need to consider those dependencies across the DNN models and need to consider resource constraints for running multi-DNN. And there are also many other constraints to consider by the system side. And for compiler, different layer or different ML operators prefers different data flow styles. So the mapping optimization needs to be carefully performed. And for architecture side, so optimizing for the average case of these kind of heterogeneous DNNs will diminish the benefit from specialization, which was the main strategy for years for enhancing the efficiency on the hardware side. And this plot is one plot from one of the recent publication impact. This shows the arithmetic intensity in the y-axis and the memory footprint on the x-axis, and each dot represent layers in many different models. And the bottom line here is that we do see diverse characteristics of operators in all of these layers, so we can easily expect heterogeneity in the multi-DNN workloads. And the main challenge is that it's hard to keep the specialization strategy for optimization, and which was the fundamental approach for DNN system optimization for years. So to solve these research questions, we recently have many works in this domain. These are examples in this domain. So Planaria, AI multitasking, Herod, and Mensa-G. So before I go to the details, the one bottom line here is that those works are pretty recent, and I'd like to highlight the emerging research opportunities in this domain. As you can see, the publication years. So that's something we wanted to highlight here. So each of them also try to focus on the types of the multi-DNN workloads we discussed in the slide 2. So although they can be extended to support all of them, but they have main focuses such as, for example, Planaria mainly targets the type 2 multi-DNN workload. AI multitasking targets type 1, which is pipeline DNNs. And Herod, which is our recent work, targets type 2 and type 3. And Mensa-G also mainly targets type 1. So as an example, we will briefly introduce the co-design problem we faced inside Herod. So to understand Herod, let me use this example. So we want to open a buffet restaurant, and customer wanted to get a steak and noodle. And we could think of 2 approaches. So one is a top chef buffet. We can hire a top chef who can cook everything 2x faster than specialty chefs and cleans the kitchen before change the menu as a professionalism, but requires a high salary. And on the other hand, we can also think about another type of buffet restaurant, which is specialty chefs buffet. We could hire different specialty chefs for each menu and distribute the cooking across each chef, and we can assign the preferred menu to each specialty chef. And the same approach can be thought in the DNN accelerators domain. So the menu is now the DNN workloads to run, and let's think of 2-layer operations: red layer and the green layer. So red layer, for example, could be a depth-wise convolution, and green layer could be a comp2D the layer. And for the top chef's approach, it corresponds to the reconfigurable data flow accelerator, which means we can reconfigure the accelerator to adapt to new layers, just like top chef adapt to each menu. But it requires high operating power for reconfigurability, and it also involves reconfigurable time. On the other hand, we can think of the specialty chef approach, which is the heterogeneous data flow accelerator, which is proposed by Harold. And this is just exactly like the specialty chef approach. So we distribute those layers across the different specialty chefs, which are sub-accelerators. So red layer goes to the red sub-accelerator, green layer goes to the green sub-accelerator. And for designing this heterogeneous data flow accelerator, it has many co-design problems. So one example here is regarding the hardware design. So if you take a look at the right side diagram, and we have 2 versions of the heterogeneous data flow accelerator. So one has larger red sub-accelerator, and the other has larger green sub-accelerator. By changing such hardware architecture, the optimal schedule also changes. So it is not sufficient to just optimize the hardware partition, but we also need to consider the optimal schedule to actually optimize this heterogeneous data flow accelerator. So this is one example we face when we work on the Herod. So I will not go into all the details of this work, but basically Herod has the optimizer that solves the co-design problem inside and reports the optimize the heterogeneous data flow accelerator. So architecture-wise, the Herod is dealing with the proposed the heterogeneous data flow accelerator. And for compiler side, it is performing static scheduling of layers, considering the hardware and many layer dependencies and constraints. And for the system side, we initiate scheduler when workload changes to adapt to the new set of workloads. So the bottom line here is this is not a problem for the one single layer compute layer, but it is a co-design problem. So other related works also is also performing co-design. So co-designing architecture, compiler, and system is an effective approach as shown in these kind of related works. And we've seen why we are getting multi-DNN by many examples such as AR glasses, self-driving cars, mobile phones. So the multi-DNN support is now a universal problem across many domains. So this gives us a kind of the huge landscape of optimization for the multi-DNN workload. So we get new multi-DNN workloads as listed in the left side. And we have a huge optimization, sorry, excuse me. We have a huge optimization space or co-design space across the deep learning model or DNN model, compiler mapping, hardware architecture, system OS. So it's a whole co-design problem, and it is necessary approach. It is a required approach for achieving high accuracy of the result and low energy and low latency of the ML system. So via this ACS and the workshop series, we look forward to exploring this co-design space with everyone. So this is the agenda of the workshop today. So this is the first opening keynote. And after this keynote, so we will have the first paper session related to embedded devices. And after paper session at 10:50 a.m. EDT, so we will have first keynote by Professor Vijay Rajanapalreddy from Harvard. And we will have a short break after that. And we will have the second paper session at 11:35 a.m. in EDT. This session will cover papers related to data centers. And at 12:20 EDT, we will have the second keynote from Bira Darvish Rohani from Microsoft. And after that, we will have the closing remark. So this is the end of the opening keynote. If you have any questions, then we are happy to answer them. Okay. I think we are exactly on time, so I think we can move on to the paper session. So we are happy to take other questions offline, so please feel free to reach out to us. So then let's move on to the first paper session. The first paper session will cover the embedded device related papers, and the first presentation will be by the Minggu Ji from Kookmin University, and the title of the paper is demand layering for accommodating multiple neural networks in memory constrained embedded systems.
Okay, hi, I'm Minggu Ji. This is a collaboration work between Kookmin University and UC Irvine. I will start the presentation. Recently, autonomous driving systems use multiple deep neural networks on a single computer. Tesla in the video performed numerous calculations and lane and object detection on a single computer for autonomous driving. Tesla's full self-driving system runs 48 concurrent networks that do 1,000 different predictions for each autopilot application, such as we live in an era where complex neural networks are heavily used. However, the number of DNNs is limited by the memory size. This is because once the GPU memory is full, no more DNNs can be added. To operate DNN, all model parameters must be loaded into GPU memory. The GPU memory responsible for inference is limited and fill up quickly after allocating a few model parameters. For example, as shown in the figure, when 3 model parameters of disk were loaded into GPU memory, the memory became full. We propose demand layering to operate more networks on GPUs. Demand layering is a similar method to demand paging of the computer operating systems. This is to bring in parameters from the disk every time it passes through the layers. Allocate and reuse GPU buffers with the maximum model parameters size among layers. As shown in figure, if the model parameters per layer of each network are constant, use a buffer in a single layer size. Therefore, GPU memory used for model parameters is greatly reduced to a total of 25 megabytes. This may be possible because disks like NVMe have become very fast to read. We targeted the darknet and YOLO networks for our experiments. First, we understood the order of operations inside the darknet. The darknet consists of n sequential layers and can be expressed by the following operations. Ri is the operation of reading the ith model parameter, and the ith layer model parameter in the disk is imported into the CPU memory buffer. Ci is the ith host to device memory copy operation, which copies the ith layer model parameters of the CPU memory buffer to the GPU memory buffer. Ei is the ith GPU kernel execution. The darknet is largely divided into an initialization page and an inference page. In the initialization page, all layers are created based on the type written in YOLO's configuration file. The weight file is read, and the model parameters all layers are copied to GPU memory. After initialization, darknet executes only kernel execution using the parameters of the GPU buffer. In this way, the original architecture allocates all model parameters to GPU memory to use the maximum memory, but only the kernel execution is operated in the inference page, so it has a fast inference speed. We know how many model parameters each layer required when configuring the network in the initialization page. Let's take an example. In the original architecture, when the read operation in initialization page reads 4 megabytes, 18 megabytes, and 10 megabytes of the 3 model parameters respectively, a total of 32 megabytes of buffer is allocated and the parameters are copied to the GPU memory. The inference page will use a buffer already allocated in the GPU memory. We try to minimize the buffer based on our analysis. The structure of this slide is the first step toward demand layering. Demand layering is a way to reuse one GPU memory buffer and use it for inference. During the initialization page, only the 18 megabyte buffer, which is the largest of each parameter size, is created. The model parameters are no longer read in the initialization page, but the model parameters are read in the inference page and copied to the GPU memory. As soon as the copy is finished, the kernel runs. This is repeated for the number of layers. Because buffers are reused, GPU memory usage dropped to a single layer level. This structure is modified so that CPU thread and GPU stream operate asynchronously in demand layering using CUDA API. Eliminate the sync time between read operations so that the CPU and GPU operation overlap a lot. However, there are cases where GPU utility drops due to the effect of second read operation. To eliminate this GPU idle time, pre-pinning method is used. Pre-pinning moves the read and copy operations of the second layer back to the initialization page, which causes GPU idle to behave like the original architecture. So the second layer of the inference stage is just kernel execution. The structure can be seen as an intermediate point between the original architecture and demand layering. We used the NVIDIA Jetson AGX Xavier and NVMe SSD as hardware platforms for our experiments, and object detection frameworks Darknet and YOLO DNN. These are the results of measuring memory usage and inference time with the structures described so far. The red star vanilla is the original architecture and preloads all model parameters, indicating maximum memory usage of 245 megabytes and minimum inference time of 174 milliseconds. The diamond in the upper left is the result of synchronous demand layering, which reduced the memory usage by 92.7% to 18 megabytes, but increased inference time by 69% to 294 milliseconds. The blue square is the result of operating this asynchronously, and it uses the same 18 megabytes, but the inference time is 230 milliseconds, which is further reduced by 27.8%. We reduced the memory usage at the expense of inference time. For tight systems like autonomous driving applications, the only option is to preload all model parameters. However, there will be systems with long cycle times, such as driver monitoring system, among many networks. System designers will face optimization between space and time when planning the implementation of multiple neural networks. And the pre-pinning method can be the control node for this. There are several pre-pinning configurations between full preloading and full demand layering in the graph. Among the pre-pinnings, the leftmost point is the result of pre-pinning the layer, causing the largest GPU idling. As I pinning the layer further, I get the remaining points where I can clearly see the space and time trade-off trend. We'll be able to determine the optimal point taking into account the space and time requirements of the application. Normally, the system is unavailable during the initialization page. The time required for initialization page, such as creating buffers and copying model parameters, is eliminated, reducing the initialization time of demand layering to 30% of the original. So Linux also has a page cache that stores the contents of recently accessed files. Therefore, when demanding layering is applied, when a file is first read or a page cache miss occurs in the middle, the worst case occurs in inference time. The above figure is the result of cache flushing during darknet operation, and it shows that the inference time increased by 39% as a page cache miss occurred. This indicates that the page cache should be taken care of if the goal of optimization is to minimize inference time. Demand layering gets model parameters from disk in the inference stage. GPU memory usage for model parameters was reduced by 92.7% due to buffer reuse. But instead of reducing memory, inference time increased by 32.2%. Pre-pinning can be also the designer's control node for space and time trade-offs. Our future work is to minimize the inference time by reducing the overhead of demand layering and to find the optimal configuration in the space and time trade-off. Thank you for listening.
Okay, so thank you for your presentation. So for audiences, please note that you can type your questions in the Q&A box. So please feel free to ask questions by that system. And I think we are strictly on time, so but let me ask one quick question. So it seems the proposed method is very effective to reduce the memory footprint, but if we have a GPU that has constrained memory for the edge device, for example, then I think the gain could be much larger. So did you have a chance to evaluate your method on smaller GPUs or on larger models?
I don't understand your question, sorry.
Oh, I meant, I think your method seems to be very effective to reduce the memory footprint. So I think the gain would be higher if the GPU has a constrained memory that cannot host all the parameters in advance. So yeah, I was asking if you tried some smaller GPUs or.
I answer in the chat.
Okay, thank you.
Okay, thank you.
So yeah, we have one question, but I think we are running out of time. So the presenters, please try to answer the Q&A directly on the Q&A box, so you'll be able to see the Q&A list there. So let's move on to the next talk. So next talk will be by Sang Bang from KAIST, and the title will be Resource-Aware Spatial Collocation for Multi-DNA Acceleration on Mobile Devices.
Hi, everyone. I am Sang-hoon Kang from KAIST, and it is a great pleasure to present my work at this workshop. The title of my presentation is Resource-Aware Spatial Co-location for Multi-DNN Acceleration on Mobile Devices. This slide shows an outline of the presentation. After a brief introduction of the topic, I will summarize three representative approaches that were published to tackle multi-DNN acceleration. Pointing out the differences between MPUs for cloud and MPUs for edge, the limitation of previous approaches will be explained, which led to the motivation of this work. The concept of this work, resource-aware spatial co-location, will be introduced with specifying the target MPU architecture. A brief evaluation will be given, followed by summarizing further works that I plan to extend. Multi-DNN acceleration has become one of the most popular research topics in the community over the couple of years. The reason for this rise in awareness is due to the widespread of DNNs. Over the last decade, due to their superior performance, DNNs took over most of the automated tasks. As a result, a neural network now is the backbone in most services. Therefore, it has become very important for modern computers to efficiently accelerate neural networks. This led to the integration of NPUs in computers of various form factors, including cloud servers and smartphones. The need for accelerating multiple DNNs on an MPU were first emphasized at the cloud scale. Because DNN inferences are embedded into most of the services a cloud server provides, it needs to handle multiple inference requests from different users at the same time. If the requests are for the same DNN, and if they are issued simultaneously, they can be accelerated on the MPU through batch processing. However, if users issue different DNN requests, multi-DNN acceleration becomes a big issue. On the other hand, many of the services nowadays require multiple DNNs in a single application. For example, translation service needs separate DNNs for different language pairs. These service requests will further increase the demand for multi-DNN acceleration on the cloud. However, demand is not limited to the cloud. For multiple reasons, including privacy, latency, and communication stability, more and more AI workloads are moving towards the edge. Therefore, MPUs integrated inside these edge devices also have to accelerate multiple DNNs at the same time. The left example shows different DNN models used in Facebook's VR device Oculus. For various vision tasks, including hand tracking and pose estimation, a number of DNNs must run concurrently. In addition, the right example shows how iPhones recognize people in their photo gallery. Face, body detectors, and embedding models are all separate DNN models that need acceleration for a single application. These examples show that multi-DNN acceleration is an important issue also in mobile MPUs. Even though MPUs inside the cloud accelerator and mobile SoC perform similar functionality computation-wise, they are designed in very different ways to meet different constraints of the two platforms. This slide shows an apple-to-apple comparison between MPUs targeting different platforms. TPU-v4 is a cloud MPU for Google with an enormous scale, and it uses HBM, which can exploit extremely high bandwidth memory interface through Silicon vs. On the other hand, Exynos is a flagship mobile SoC from Samsung, which integrates 3 MPU cores. It uses LPDDR5 memory, which is a state-of-the-art memory technology for low-power devices. If we compare the two, TPU integrates 48 times larger on-chip memory and can use 12 times higher external memory bandwidth. Due to these differences between MPUs for cloud and edge, adopting previous approaches for multi-DNN acceleration on the cloud is not available on edge devices. In case of temporal multi-tenancy, in order to overlap the latency, on-chip memory must store waits and activations from different DNNs. Due to the limited on-chip memory size, this approach is not suitable for mobile MPUs. The spatial multi-tenancy proposed in Planaria exploits extremely high external bandwidth when co-locating multiple DNNs. This will lead to resource underutilization when adopted to mobile SoCs with limited bandwidth. The heterogeneous architecture with sub-accelerators can be highly efficient when target workload is fixed. Therefore, this approach is suitable for application-specific edge devices. However, it is not suitable for general-purpose mobile SoCs where there is only a single user occupying the hardware. With a single client, we cannot guarantee a fixed set of workloads, which will lead to low core utilization. This slide shows the concept of this work. The objective is to enable multi-DNN acceleration for mobile MPUs that can be integrated in mobile SoCs. We selected a coarse-grained reconfigurable MPU for the target architecture to maximize the utilization without much hardware overhead. Based on the target architecture, we propose a resource-aware spatial collocation method to avoid core and bandwidth utilization drop due to load imbalance between heterogeneous workloads. Also, a two-step workflow incorporating compile time and runtime support is proposed to adapt to variable effective memory bandwidth, which is a unique characteristic of mobile SoCs. The details of the proposed concept will be shown in following slides. As a target MPU of this work, we have selected a coarse-grained reconfigurable architecture, which integrates a fixed data path inside each core with inter-core reconfigurability. A total of 16 cores are connected with a mesh network sharing the external gateway. Inside each core, 72 MACs are integrated, which are fixed to a parallelism in channel dimension. The target specs are like the following. Target MPU picks at 2.3 TOPS per second throughput and 51 GB per second external bandwidth with small on-chip memory size of 1 MB. Even though data path inside each core is fixed, the inter-core reconfigurability can fill cores with computation tiles and minimize idling PEs even with different layer configurations. Adopting reconfigurable mixed division from previous works, the MPU can switch between channel and activation division to exploit maximum parallelism. If the layers are divided in channel dimension and allocated to different cores, NVDLA-style channel parallelism can be exploited. On the other hand, if the layer is divided in activation and allocated to different cores, CDNO-style parallelism can also be adopted. Based on the proposed target MPU architecture, this work proposes a resource-aware spatial collocation. It tries to tackle a load imbalance problem suggested at AIMT. When accelerating multiple DNNs, if all of the cores are allocated to computation-intensive workloads, the MPU's bandwidth will be underutilized. On the other hand, on the right, when running data-intensive workload, because of the memory bottleneck, even though all the cores are allocated to the workload, the core utilization will be low. In order to achieve high utilization of both core and memory bandwidth, spatial collocation of different workload is proposed. With majority of cores allocated to computation-intensive workload and the rest allocated to memory-intensive workload, the two workloads can share the external bandwidth. As a result, the heterogeneous workload can compensate each other's bottleneck, achieving high resource utilization. This slide shows the concept of spatial collocation in famous roofline model. The dotted line indicates the operational intensity determined by the MPU's hardware specification. The blue task located left of the line is data-intensive task, which is bandwidth limited, and the red task located right of the line is computation-intensive. The proposed collocation aims to merge the two tasks and move the operational intensity close to the MPU's ideal intensity. Following the roofline model, to define whether the target task is data-intensive or computation-intensive, we use operational intensity of the workload, which is dependent on the layer's configuration. The algorithm on the right shows a characterization flow of the workload. If the task's operational intensity is smaller than the alpha over bandwidth minus delta, it is considered to be data-intensive. The hyperparameter alpha is a hardware-dependent parameter, which is proportional to the peak performance of the MPU. And delta is a parameter defining the margin around the decision boundary. Therefore, tasks above the boundary is regarded as computation-intensive. If the target task falls inside the margin around boundary, it is regarded as an ideal task that can maintain high utilization without collocation. Here, it is important to note that bandwidth is not a hyperparameter, but an input parameter to the function, which leads to the next important issue. In case of cloud accelerators, they have dedicated boards and dedicated DRAM for the MPU. However, it is totally a different story for mobile MPUs. The range of functionality of modern smartphones is very wide. To support these wide functionalities, the modern SoCs integrate a number of different IPs inside a single die. The IPs include CPU, GPU, ISP, MPU, modem, and many more. Therefore, these IPs inside the SoC have to share the external DRAM interface, whose bandwidth is already very low. Sharing the bandwidth will further limit the effective external bandwidth an MPU can exploit. Furthermore, how much of the bandwidth an MPU can exploit is unpredictable. Tasks such as frame rendering, video encoding and decoding are handled in different IPs inside the SoC, but they will require excessive amount of memory access, in turn which will limit the accessible bandwidth of the MPU. This concludes to a design challenge that effective bandwidth that the MPU can use is unknown when the developer deploys a DNN-dependent application. The change in effective external bandwidth changes the characteristic of the tasks. If we revisit the roofline model, reduction in bandwidth can change what used to be a computation-intensive task into a data-intensive task. Merging two data-intensive tasks cannot increase the resource utilization, leading to failure of collocation. Therefore, it is important to characterize the tasks correctly, depending on the effective external bandwidth when the tasks are running. However, the effective external bandwidth cannot be identified at compile time. Therefore, we propose a two-step workflow to realize the resource-aware spatial collocation. It needs the support from both compile time and runtime. At compile time, operational intensities of all the layers in the DNN are calculated and stored in the intensity table alongside the binary for execution. The intensity table is utilized at runtime by the runtime scheduler to characterize whether the task is computation intensive or data intensive on the fly. At runtime, the current bandwidth of the SoC is monitored and used as the input parameter of the characterization function. Based on the characterization result of multiple DNNs, the scheduler determines whether to collocate the task or not. This slide shows the decision flow inside the runtime scheduler. Layers which can maintain high utilization on its own comes into the highest priority. If the layers fall between the decision boundary of the characterization, it is considered as an ideal solo run candidate and executed without collocation. Next in line is a dual run. If the upcoming layers from different DNNs are of heterogeneous characteristics, they are collocated on the MPU for a dual run. If one of the layers finishes earlier than the runner-up's characteristic is identical, the dual run automatically extends to the next layer. Here, if DNN B's layer 0 finishes earlier, layer 1 will take over the baton to run with DNN A. If there is no dual run candidate left for the upcoming tasks, scheduler look for potential dual run candidates. Here, DNN B's layer 2 is a potential dual candidate because it can be paired with layer 3 of DNN A. On the other hand, there are no layers left for DNN A's layer 2 to pair up with. Therefore, it is classified as helpless solo and executed without collocation. Even though the resource utilization is low during helpless solo runs, it will increase the possibility of layer pairing. The proposed resource-aware collocation method is benchmarked using 4 different DNN models, including ResNet, VGG, MobileNet, and MobileBERT. We synthesized 6 different workloads with different pairs of DNNs and ran under 2 different external bandwidth conditions, including 51 GB per second and 31 GB per second, which corresponds to LPDDR5 and 4's external bandwidth. This slide shows the benchmark results. A meaningful increase in overall latency can be achieved. A maximum of 1.32 times speedup is achieved when running ResNet alongside mobile BERT. This can be an expected result because overall, ResNet is computation intensive and mobile BERT is bandwidth limited. In addition to adopting spatial collocation with 32 gigabyte bandwidth, can most of the times achieve higher speed than 51 gigabyte per second baseline. However, if two memory-intensive workloads are paired, which are MobileNet or mobile BERT, no meaningful speedup could be observed. The content of this presentation were regarding an ongoing research. Therefore, I dedicated most of the time on explaining the motivation and basic concepts. Through the review process of this workshop, I received meaningful comments from the committee members suggesting directions for further evaluation. And I really thank you. Thanks for the valuable suggestions. Based on the comments, I am planning to conduct a more thorough evaluation on energy consumption, comparison with previous works, and evaluation on different hardware configurations and workload configurations. In conclusion, the motivation of this work was to propose a method for multi-tenant acceleration at the edge. Because previous works were focusing on cloud accelerators, they cannot be adopted to mobile MPUs, which are highly limited in terms of on-chip memory size and external bandwidth. To maximize the resource utilization under multi-tenant workloads using coarse-grained reconfigurable mobile MPUs, we propose a resource-aware spatial collocation based on two-step workflow, including compile time and runtime support. Thank you for your concentration. If you have any questions, please feel free to ask. Thank you.
Okay, thank you for a great presentation. It seems we have one question on the Q&A. So the question is, does the scheduling logic needs to be present on chip?
Yes, I believe the scheduling logic needs to be located on chip. At our current development level, we didn't implement the scheduler in Verilog, but we simulated the scheduling in behavioral models. But if we extend this research for development, I believe that the scheduler has to be inside the hardware.
Okay, thank you. So because we are behind the schedule, so sorry about the other questions. So Sang-Eun, please answer the questions in the Q&A box offline.
Yes,
and,
thank you.
Yeah, so thank you for a great presentation again. So we'll move on to the keynote. So Tushar, please.
Yes, thanks, Yeokjun. Thank you to the speakers of the first session. So next we'll move on to our to the keynote. So Vijay, are you online? Can you hear me? Can you see me? Oh, perfect. Yes. So it's my great pleasure to introduce Professor Vijay Reddy from Harvard, who's graciously agreed to to give a keynote. And Vijay probably needs no introduction to the attendees. And I was reading his bio, and I was like, probably just reading his bio will end up taking the entire half an hour. So, but just to kind of set some context, Vijay is an associate professor at Harvard. Of course, he's a founding member of ML Commons, a VP of that, and he's also been very actively involved with ML Perf. And I think most recently, he's been doing a lot of interesting work related to Tiny ML. And today he's going to talk about the idea of democratizing Tiny ML. So Vijay, you can kick it off.
Awesome. Thank you, Tushar, for having me here. It's a pleasure being here. All right, so today, my focus really is to kind of generally introduce the notion of Tiny ML, some of which you might be familiar with, but I'm trying and specifically focus on interesting applications that are coming about this deeply embedded machine learning space. So I'm going to first and foremost introduce it as a concept, and then I'm going to talk about some of the interesting challenges that we have in this space from a systems and hardware sort of standpoint. And I'm going to talk about it at a systems kind of level, because I think very often people kind of miss a systems sort of a perspective. And that often has great implications when you want to really enable this sort of ML at scale. And I'll get to that in a bit. And the third point I actually want to get to is kind of like intentionally shift some of the focus that we have typically around like, architecture venues, thinking about like the core ML part. I'll intentionally shift you all into thinking about the data itself, actual data, and how the data set is curated and what the implications of how we curate these data sets are. Because I think that shift from being very model centric in our community needs to kind of also start to embrace more of the data centric approach, because these two things are really coupled together if we want to enable any kind of ML. More on that. So those are three sort of primary goals. Let me first and foremost start off by talking about what do I mean by TinyML, right? TinyML is effectively embedded machine learning. You got embedded systems in the traditional space, and now what we're doing is trying to bring in machine learning onto these embedded systems. And it's arguably one of the fastest growing areas because of the very large and distinct number of use cases, some of which I'll show you. Fundamentally, it's about the intersection of machine learning algorithms, embedded hardware, and embedded software, which is where some of the beautiful technical challenges will start emerging when we start to fuse all these things together. And the key nugget of why we want to do this is to really focus on on-device sensor analytics. Effectively, what we're trying to do is move the compute closer to the data. Specifically, with embedded systems, you're dealing with sensor data, be it an audio stream, a video stream, a motion stream, some sort of pressure, temperature, some sort of time series signals that are going by. And the reason we want to do this is because it's got bandwidth savings, energy efficiency savings, reliability aspects, better latency or performance. So there are many, many reasons as to why you want to do on-device sensor analytics. And the whole intent is to ultimately do this with ultra-low power consumption so that the machine learning tasks are running continuously, right? And in a perfect world, TinyML would ideally be operating on battery-powered devices, which is extremely critical if we want to enable machine learning at extra scale, right? At the extreme endpoints. The most common example that we all take for granted is really around applications like this, right? Like when you say, hey, Siri, that is a textbook style keyword spotting example of TinyML running on device, be it on your watch, be it on the Alexa device that you have, or your Google Assistant. The whole notion of watching for that critical keyword in order to wake up the rest of the big SOC subsystem is sort of what TinyML is. And this is just one of the example applications. This is one we take for granted. But increasingly, as we go into the future, we're going to start seeing the sort of embedded ML, which we're finding on endpoint devices, be spread across all kinds of different devices in our community, in our homes. For example, like I like to cook a lot. So I could imagine walking up into a future kitchen and being able to just say, bake at 350, toast for 2 minutes, right? It's what we call as limited vocabulary capabilities on endpoint devices. My toothbrush, for instance, is definitely a smart device. It's got some kind of machine learning, not necessarily deep learning, but machine learning that's actually doing in order to give me recommendations on how I should brush better, right? And our smartwatches already have some sort of ML in order to try and figure out when to do what to do, right? Now, these are common applications that you might have heard about. Now, I'm also going to try and push into some emerging applications that you might not really be familiar with, but which are really wicked cool. And I want to talk about those because I'm going to try and connect that over to the multi-DNN aspects. One of the key things is that one of the reasons I chose to kind of talk about this space around embedded ML is because when it comes to embedded ML, we haven't seen that much multi-DNN stuff out in the world yet, but we're starting to move towards the transition. So I'm hoping to kind of get you all excited about the possibilities that are on the cusp for multi-DNN acceleration. So this video, for example, is about Gamer. This is something that we worked on within Google. I also consult with Google. So this is a project that we've worked on where the whole intent is to get your shoe to be smart. It's a next generation shoe. I'll play just a little clip of it to kind of get you to start thinking about the possibilities of what kind of. Quick question, are folks able to hear me? Because I don't know if I enabled sound sharing.
Yeah, we can hear you, but I can't hear the audio from the YouTube clip.
Yeah, so let me just reshare. That's because I didn't enable sound sharing. There we go. That's going to fix it. Yeah. Okay.
All right, sitting down now. Right. Repeat after me. What you do in this world echoes.
So this is a project called Jacquard at Google, a team that we work on with Google and Adidas actually paired up together. The whole intent of this exercise is that we actually want to enable machine learning on that small little device that you saw, that black chip that they were pushing into the shoe. And it's actually performing a variety of different tasks. One of the things you can imagine that it's actually doing is basically it allows you to, you put the device into it's a small little microcontroller that's actually running a bunch of different machine learning models. And what it allows you to do is to actually collect interesting stats when you're playing soccer. Effectively, it figures out how many kicks are you doing, how fast are you kicking, are you doing a penalty kick, and if so, how well did you do the penalty kick? Because it's a very different motion from just kind of running and kicking. And if you're passing the ball, how many dribbles did you do, and so forth. So just in this sort of like very simple embedded device, right, which you're putting into a smart shoe that you can actually buy today, by the way, you have to run multiple models concurrently, which makes it really interesting to try and figure out how do you sort of on an embedded device, which has only maybe around 64 kilobytes of SRAM or maybe 256 kilobytes of SRAM, how do you get these multiple models to actually work? I'll get into some of those challenges later on, but specifically what I'm trying to indicate is that these are some of the really interesting applications that we're starting to see where you're having to do multi-DNN stuff on deeply embedded systems, and it has to obviously be very efficient in terms of how it's actually running this, right? Now, this is in the context of shoes, for instance, but there are also really interesting works in the context of what we call as tiny robot learning that my group has been actually working on, where what we're really doing is running small little machine learning models, which are actually running, in some cases, concurrent models, where the intent is to specifically be able to go and locate a source. So for instance, just to kind of make it concrete, so in this particular example, this video, what we're showing you is sort of like a nano drone, right? That's got some sort of flight capability. And one of the interesting things that you have to do in these kinds of things where, for example, this drone, which might be used in search and rescue or something like that, is trying to navigate and try and find a particular course, a particular source. On the left-hand side, it's trying to find a light. So that's why it's kind of constantly moving towards a light source. You can imagine it could be some kind of signal that's being emitted and it's trying to track the signal. Now, tracking the signal is just one part, right? But it's also got to avoid obstacles while it's going. So you can do this through a multimodal sort of a network where a single big network is capable of both avoiding obstacles and keeping track of the source, or you can run multiple networks, multiple separate networks. And one of the really interesting problems that we ran into when we started deploying this on these systems is that we often tend to focus on just kind of like running the core models and how well the models does. But in fact, just like in the the first presentation where we saw with this Tesla running this autonomous car, which you often get into is there are several real-time constraints, right? You've got a flight control stack down here that is running. Now, this flight control stack may be a machine learning model. In our case, it was not. It was a traditional PID-based controller. But you often get into this issue of you're trying to run the network while you're also trying to run something else at the same time. Now, in the similar case on the right-hand side, this is looking for light, this is looking for gas, doesn't matter what the task is. But the point that I'm trying to get to is that when you're starting to run embedded ML on very small devices, because these devices are extremely resource constrained in terms of power, performance, and memory, what you get into are issues with having to juggle for real-time capabilities. And I think that's a really interesting area of research that is yet to open up. And we found some of these challenges because we started trying to just use machine learning models to demonstrate application capability. But very quickly, we realized there's a massive systems problem in here. So hopefully people kind of see that some of the interesting applications, like the ones I'm showing you, actually really require multi-DNN support, but this is on an embedded microsystem.
There's a dangerous gap.
Another one could be an interesting application that we're doing with some wildlife conservation related project is trying to, for instance, help preservation of these big elephants that are actually dying at quite a remarkable pace, right? And the intent is you want to be able to build small embedded machine learning devices and be able to tag these big creatures with these devices, so that in the field you can actually try and do some sort of detection about what they're doing. You can do tracking, for instance. You can do monitoring of where they're moving. You can do conflict resolution, because often these animals get into spaces with humans. So if you kind of know, if you're able to track them, then you're in real time, right? Then you can actually alert park rangers. Or there are also really interesting things you can do, which is actually try and understand what activity is happening in wildlife. And I'll talk about some interesting challenges here with respect to multi-DNN stuff in a second. So in this video, what you're basically looking at is a spectrogram at the bottom, and the spectrogram has got a certain, it's a frequency domain signal of whatever sound that the elephant is making, right? This is effectively keyword spotting, right? When I showed you, hey Siri, it's the exact same kind of thing. It's just that the model here, for instance, could be used to detect this particular sound. Now, why is that an interesting application for TinyML? Well, it's because in this particular case, the infant is actually lost, right? So it somehow got separated from the actual main tribe, and it's actually trying to look. And if you can embed small little TinyML devices on these kinds of animals, then the beautiful thing is that obviously you're not going to be able to replace battery and so forth. So you'll actually be able to, track them in the wild for long periods of time, because you can't go in and replace batteries every couple of weeks, right? So it's all about the efficiency aspect. In this particular case, what I'm showing you is that you can deal with sounds. Obviously, you can do keyword detection in this, and then you can use something like a low power LoRaWAN connection to be able to transmit important signals off of the device to park rangers. Or there are many other different concurrent use cases. You want to be able to do activity detection. The activity detection could be like being lost, or it's actually eating or sleeping, and you can start building a really interesting profile of what's actually happening. And so TinyML enabled some of these really interesting applications for consumer things like automating your kitchen, or it could enable applications for health for us, like with your activity, for example, when you're playing soccer and you're monitoring all this stuff. Or it can actually enable a lot of interesting use cases in wildlife, as well as robotics and so forth. So lots of really interesting applications, but all of them end up actually requiring multi-DNN support, which in fact really doesn't quite exist today in this particular space. So these are some of the activities that I was mentioning you would want to do concurrently, for instance, in this Elephant Edge project, where you're doing risk monitoring, conflict monitoring. What is the exact activity? What is the communication that's happening between these wildlife creatures? And the point that I'm ultimately trying to get to is the fact that when you look at a lot of these kinds of applications that I'm talking about, they're really sensor driven. And if you look at a lot of the IoT devices, there's an insane amount of data that they produce. And today we harness less than 1% of this unstructured data. So despite all the fancy use cases that we talk about, like being, classification, detection, segmentation, recommendation systems, there's an entire domain of field that's just waiting to be unlocked. But as I'm showing you, in a lot of these applications, you actually will need multi-DNN support, because it's often these sensors are trying to perform multiple tasks. So now that you sort of have an idea about what this sort of space is about, I'm going to try and talk about how do we sort of enable this sort of ecosystem at scale? How do we actually technically start getting machine learning at scale in embedded devices? Now, I've kind of cherry-picked 3 core concepts that I want to touch on today. One is about generalization, which is dealing with the extreme heterogeneity that we have in embedded systems. Then I'll talk about standardization, is how do you accelerate innovation in this particular space so that the industry and academic research can actually be driven faster? And how do you enable the data-centric movement, which is not specifically focused on models, but rather focused on the data that you actually need? Because a lot of us focus on models, and I often think that it's a misguided perspective. Because look, if you want to practically solve a problem, no one's going to have a data set sitting on some URL that you can just go download. So you have to figure out how to solve the data set problem in order to really get some of the machine learning tasks that we want to enable in this space. So I think it's an important thing I'll touch on. So talking about generalization, so I'm gonna get into the systems aspects here. One of the key things when you're looking at TinyML devices is there are a lot of different embedded systems, and there's a remarkable amount of fragmentation and heterogeneity in this particular space, right? A lot of these devices, one of the beautiful things about these devices is that there are many, many of them. Already there are about 250 billion microcontrollers just all over the planet, and around tens of millions of microcontrollers are often shipping every single year, all of them being ARM, of course. Now, one of the interesting things that you will notice about a lot of these devices is that they're highly fragmented and they're really sort of unique in their capabilities. So here I just kind of cherry picked 4 different, systems, right? And if you look at the MCUs here, they often, some of them have DSPs, some of them will have like, in this particular case, they're all 32-bit, but that's actually not the case. You might have 8-bit, 16-bit microcontrollers. You might have FPU support. You might not have FP support. You might have SIMD support. You might not have SIMD support. So it's very, very different than the traditional homogeneous ecosystem in which by and large you're playing. The previous talk kind of touched on mobile SoCs being fragmented, which is true. There are lots of acceleration capabilities. And if you look at multiple SoCs, they're very different. And you take that and you look at the embedded ecosystem, it's much more fragmented. And so this leads into a serious portability problem because code that you often run or compile down to one particular MCU is not going to be portable across another device. Tell me when was the last time you ever worried really about code portability? Most of the ecosystem is just kind of running on x86 code, right? So you often don't think about the issue of, hey, how can I get a model which once I compile down to one particular architecture, how will it actually run on another embedded system? We actually don't think about it, but it's in fact one of the key limiting factors to enable TinyML at scale. And these devices, of course, have various capabilities in terms of performance, very, very limited amount of RAM, right? And the flash is also extremely limited. So we're talking about models that are often in the order of a few kilobytes, not megabytes, things that we often take for granted. They come with very different sensors. These sensors have a lot of heterogeneity in them. Even if I have a microphone on one particular device, that microphone is going to be inherently different from another microphone on another embedded device. And all of this actually becomes a real big problem when you're trying to run ML in production use cases. And the last thing is around connectivity. Connectivity is also something that we often take for granted in a lot of big systems. But imagine when you're deploying TinyML into like remote places, right? Now, what are you going to do? If you can't extract the data out of that thing, then you've got a problem. But if you do want to extract the data off of that device that's on an elephant, well, then you need radio connectivity. And the second you introduce radio connectivity, well, almost 50% of your power budget just goes up because you have only half of it limited for compute to run the models. And then, of course, then, it depends on how often you're connecting to transmit data back to park rangers and so forth. So these kinds of problems are serious issues in terms of actually enabling TinyML at scale. It's nice and cute to be able to write a paper that you got something running on a particular device and you can claim state of the art, but this doesn't often translate into real impact in the field because when you build models, they often get stuck on a particular device. You're bound so tightly into a single platform because of efficiency needs, right? Every particular device is highly tuned. So I'll kind of quickly summarize some of the challenges that we generally get into here. So broadly, the challenges with the embedded ecosystems are like you have hardware challenges or you have software challenges, and you have to kind of deal with both in order to somehow be able to deploy machine learning at scale. Now, for example, if you look at the hardware space, one of the key things is keeping that need for efficiency. What ends up happening is that there's a lot of specialization that's done at the embedded microcontroller level. For example, if you just take the hardware is extremely heterogeneous. There are a lot of different like embedded chip architectures in active use. Like there's the ARM Cortex microcontroller class, then you have Tensilica DSPs, you have Qualcomm DSPs, Seva DSPs, Synopsys microcontrollers, like on a whole range of Texas Instrument-based, very ISA specific sort of implementations. More so than just all these different companies that you have, one of the key problems you have is that the ISA is super specific to a given version of the embedded MCU that comes out. The instruction sets are often incompatible, like on a single chip over its own generations, the ISA is incompatible, right? So which means if you compile something down to one particular device, then you'd have to do the whole recompile for another variant of the device. You can't just take the code and run on, which means code portability becomes a massive nightmare in these devices. And there are also, of course, resource constraints. Memory, as I showed you, is extremely limited. We're talking about in the order of like, a few kilobytes of SRAM, and your flash is also very limited. And of course, power is extremely key. On the software side, simple things that you would take for granted don't even exist. Like if you think of something like memory allocation, when was the last time you ever really worried about memory allocation? Well, on embedded systems, if you talk to deployment scenarios, you'll see that you can't even make basic assumptions about memory management. And often embedded system developers will say, unless you can guarantee me that your machine learning model is never going to run out of memory in the application that you're deploying, I'm never going to deploy it because I need to know that it's always going to work 100%. I cannot risk any kind of fragmentation in memory in a certain collapse because getting an embedded device back is virtually impossible if you break it. And of course, you don't have operating system support. And even if you have this, again, for portability reasons, you don't want to actually support these kinds of things. So one of the projects that I worked on was is what we call a TensorFlow-like micro. It's basically TensorFlow designed for microcontrollers. I won't get into all the nitty-gritty details around this, but at a very high level, it's specifically designed to run on embedded systems, and it can actually support a wide array of different systems. And it's got a very, very small footprint in terms of memory, in terms of the binary footprint. And we don't rely on dynamic memory allocation, no dependencies on any types of libraries, no operating system dependencies, and everything is assumed to run bare metal. You can read our MLSys paper. It gets into a lot of technical details about how we actually have to engineer this thing. And one of the cool things about this particular thing that is counterintuitive in its design, I'll just pick this one particular thing to talk about, is that it's actually an interpreter. You would think like, traditionally, if you know anything about compilers and interpreters, you would think like interpreters are really, really bad. Interpreter basically means you're executing a program by following some kind of data structures that's kept in memory, instead of doing a fully compiled sort of an approach. And this means that what you're doing is you're keeping the model separate from the actual code that's actually executing it. So you're interpreting the model on the fly. Now the convention here is that interpreters are terribly slow. Think of Python, right? Python is like several orders of magnitude slower than running a compiled piece of code. But then why in the world would we ever want to actually design an interpreter for an embedded system? Well, the reason is because one of the things that you can do is that you can actually keep portability. You can update the model. For instance, if this is the actual instruction for the interpreters, the dispatch loop kicks in, it actually reads what the network wants to do, that actually has some runtime operations that are device specific, but the model and the interpreter itself can be completely independent. And this allows a massive amount of portability. I can get into a lot more detail during Q&A if needed. Traditionally, interpreters are really bad because they're often slow, because the overhead of basically reading an instruction, figuring out what the semantics are, and then decoding it, and then actually performing the functional operation needed for an instruction is why Python is, for instance, very slow compared to C or C++, right? But machine learning is inherently different. The fundamental observation that we made was that, look, when you look at the graph and you actually look at the operations or the instructions you have, they're massive, right? For example, if you take a convolution, you're going to spend a massive number of cycles actually executing the convolution. So the overhead of actually doing the parsing to figure out that you want to do a convolution is really, really small. And if you look overall across any kind of network graph, right, you will find that that overhead ends up being very little dispatch with respect to the amount of time you actually spend within each and every single op. Just to kind of put these things into a concrete perspective, I'm showing you that the overheads can be as little as like 0.1% or maximum about 4%. And the key thing is that the interpreter allows you to change the model on the fly, which is extremely important. Often when you take any embedded systems, what ends up happening is the embedded systems are extremely tethered down to one particular sort of device, because you have to compile it down to it. And instead, in this particular case, what we're able to do is to actually allow the code to run independently. And this effectively gives us portability, and that's extremely key. In other words, whatever code you compile to run on one particular device ends up being able to run on any other device. And one of the cool features that I encourage you to go check out in the paper we talk about is specifically how do we support multi-tenancy for different neural networks on MCUs, right? That shoe example, for instance, that I gave you actually turns out like you actually have to run 4 different networks in the Jagger inside that Jagger chip and that for the added S chip. And one of the key things is that you have to support these multiple networks. And so one of the ways we do it is by actually understanding what's the biggest size of the network, how much are the intermediate values that you're holding, and according to that, we do some sort of optimizations in order to support multiple networks at the same time. Again, we can do this by knowing things ahead of time, so it's not like you deploy something and then something ends up breaking. So that's sort of key. Another thing that I'm going to touch real briefly on is around just standardization. One of the key things is that when you're running models on machine learning systems, which models should we all study as we are trying to do any kind of work in TinyML, for instance. Turns out the system is extremely complicated, as with any inference system. It's actually a very complex landscape because there are multiple layers within the system stack, right? Different engines, different hardware, different sensors. And there are also many different kinds of use cases, right? So how do you sort of distill which are the most prominent and important things to study? So to this end, one of the things that we had done was we actually brought the industry together to answer 3 fundamental questions, which was like, what use cases are the most important in TinyML? How do you support the innovation in this space? And how do you sort of evaluate it according to the right set of metrics? So we brought a large number of industry members together, and through community consensus, we ended up driving 4 important workloads that we feel like both for research and academia, research and commercial purposes. Keyword spotting, like Hey Siri and so forth, visual wake words, detecting if there's some sort of person or activity in a particular picture, anomaly detection, if a motor is about to fail, being able to say, is there some sort of anomalous signal in a time series data, and just small image classification, like your Ring doorbell, being able to say there's a person or a cat or something like that. So these are the different use cases that we actually ended up building. And one of the things that I want to do is skip ahead a little bit. And so out of these benchmarks, what we do is we run a competition on, industry comes together and benchmarks on this. And one of the things that I want to highlight are sort of like, what are some of the interesting findings we make? People have used the benchmark, for instance, to design custom microcontrollers that can handle these different networks. They have done software-only optimization that is completely agnostic of hardware or microarchitectural level changes. Then, people have also designed custom neural network accelerators like Sentience that runs keyword spotting, for instance, in I think like about 150 microwatts, which is remarkably efficient. And then people have also used it to demonstrate that no matter what the network is, we can effectively build a custom hardware accelerator on the fly on an FPGA. So these benchmarks, once you curate them, actually enable the community to actively participate and show different kinds of use cases. And one of the interesting things that we're actually starting to work on right now is like looking at multi-DNN sort of workloads that are specifically on embedded devices. There is no official benchmark for this, but we're in the process of kind of seeing what would be some interesting use cases where you actually have them. One of those examples is that shoe example where you need to be able to figure out, are you kicking, are you running, and those kinds of things, each one being a very small model, because a single monolithic model ends up being a little too big. So actually splitting it into smaller ones actually makes more sense. I'm curious, Kushar, how much time do I have?
So we have officially we said till 11:25, but then we have a 10-minute break. So I think you can go on for a few more minutes. Maybe if you can wrap up within 5 minutes, that'll be great. So we'll still have some time for Q&A and jump back to the schedule.
Awesome, thank you. The next thing I actually want to jump on and talk about a little bit is around data engineering, thinking about data sets. So this is something intentionally that I said is not going to be model centric, it's not going to be architecture centric, but I think it's extremely important if you want to enable interesting research in the field. So typically, for instance, right, oops, sorry, I think I jumped too far ahead. Oh yeah. So let's say you take this example of Hey Siri, right? Or you want some sort of consumer use case where you actually want to enable some TinyML application. One question is how can you enable this in a wide range of different languages? Because often when you're interacting with conversational AI systems, you're only dealing with a single language. Often you're just dealing with English, but there's 7,000 different languages spoken on this planet. So are we just going to ignore all of these languages as we build AI systems, or do we actually think of how we can enable multilingual capabilities on endpoint devices? This often means that you need data, right? For any speech thing or any vision thing you want to build, you have to build data sets. But the problem is that when you look at, for example, in TinyML, if you're looking at speech kind of thing, As you try and factor more and more people across the planet, you'll find that the volume of data that we inherently have, the data sets that we have in order to build models and then build hardware for those, diminishes extremely fast. And one of the problems is really that it's about data engineering. If you want to build a data set, you got to gather the requirements. You have to have a clean set of requirements. You have to have like the right sort of gathering process, making sure there are no biases in the data. There's no people are labeling correctly and you know what to label. Then you've got to make sure that the data is actually correct. Whatever data you got that was collected is actually correct. And then over time, data ends up drifting. Like, things change in the world. So you have to maintain that data set. This is an extremely costly and tedious process. And the way we do it, state-of-the-art approach, by and large, I would argue, is like, we do it through construction by hand. In other words, we often have people that we hire and then we build data sets. Well, the key question is this: how can we democratize this kind of data engineering practice, right? How do we convert this sort of, someone's going to build the data and we don't think about it? Well, I really think if we want to build better models and enable this sort of an ecosystem, then we have to democratize the data engineering pipe itself. So for example, let's say, in the TinyML use case, I have a device that's able to recognize yes and no. Now I want to do this in many different devices. Today, you would go and download Google speech commands or your favorite data set, and then you would run your model and then you would show results. Instead, what we want to do is try and build an automatic data set generator, where effectively what you really want to do is you want to specify the task you want. For example, I want yes and no words. And then the system automatically searches the web in order to find sentences or corpuses that are available that have the keywords embedded in them. Right, so this might be a full sentence. He gazed up at the steep bank, and out of that you extract the keyword that you're interested in, and then you run this at scale on the fly. Right, it's like building a Google search engine effectively for the data you want, and it curates a data set that you need on the fly, and automatically then you train a model on it. So in other words, it's actually how do you dynamically get the data that you want in order to train the model. This is actually really interesting because it opens up a really interesting space where how do you do data set generation coupled with training the model so that the training and the data generation actually results in a much more efficient model. So we built some system like this where I'm showing you, like, with the push of one button, we synthesize data across many different languages where for the first time you're actually getting a data set in order to do something interesting. And in high resource languages too, where you have lots of data, we create this data set completely on the fly. This is just showing you a long tail of different languages. And one of the cool things about this is this newspaper that is out this year, basically talks about what we call as a multilingual spoken words corpus, which shows how to create data sets on the fly for a given task. Now, obviously, we do this in the context of the TinyML use cases because that's the domain that we care about. But effectively, we built an automated data set generation pipeline. We've done this for speech. Now we're actually looking into doing this for vision. For specialized domains. So if you do that, then the next step would be actually how do I do the data set generation and know when to stop because the data is just good enough, and then train the model. Effectively, you don't want to just assume a certain corpus is the right amount of corpus. You actually want to intelligently subset the corpus. You want the smallest training data set that is also of the richest value, which can then result in the best model. Which means end-to-end solution is actually what you really care about. The end-to-end solution is not about just how you run the model. It's actually about how you get the data and then you get a fine-tuned model. If you want to democratize this sort of technology, you have to build those kinds of pipes. And this is actually an interesting opportunity for systems community to be looking at. No one has been looking at how long it takes to build the data and whatnot, because we often just go assume that the data magically pops out for us and we just run the network. But I think over the next 5 years or so, we're going to see a lot more emphasis being put on this sort of data generation. One last thing I want to mention is that I'm also very passionate about education in this space. And so, I encourage people to check out this paper where we talk about how do you get machine learning capabilities into the hands of people, and how do you do this across at a global scale, right? So we've been we're working very closely with Google on this and trying to figure out how do we teach applied machine learning. And not just the model engineering, but actually showing them the full cross stack that you need to have, which goes from data engineering to model deployment, which is a very complicated pipe. And often a lot of us just get caught up in the model engineering part and forget the rest of the stuff. But the rest of the stuff is just as critical. It's incredibly amazing, even within Google, I've firsthand seen use cases that failed because there's a semantic gap between model engineers and then the actual developers who are pushing the models into production, especially in TinyML use cases. So I know I kind of covered a lot of ground and I did this really fast, but hopefully the key things you take away is that TinyML has got really set of interesting use cases. Many of these use cases are increasingly going into multi-DNN stuff. And I talked about we have to deal with some of the hardware heterogeneity problems, which I think is an opportunity that is wide open for a lot of research contributions. Talked about standardization and picking benchmarks that are representative. So far, a lot of the communities just kind of focus on single benchmarks, like for a particular task, but there's pathways opening up where we're starting to understand what are the multiple tasks that we actually want to do on device. And finally, I touched on this notion of if we want to actually enable interesting work being done in space, we have to focus on data set generation itself. And interestingly, the data set generation coupled with pre-processing, coupled with the model building, that cross product results in much better machine learning models than if you just considered pruning, quantization, and all those kinds of boring things in the model space. With that, I'll stop and turn it over to Tushar.
Thank you so much, Vijay. That was a really, really, as you said, like a lot of information, a lot of topics you touched upon. Thank you so much. I think this was very, very useful. So the floor is open for questions. Like for the audience, please type your questions in the Q&A box. For some of us who are like panelists, we can just ask live. I'll maybe just kick it off by, so the thing I really like, Vijay, one thing that stood out was also you talked about benchmarking in this space. So as you mentioned, like, within the TinyML context, thinking about what might be benchmarks is really interesting. So maybe a couple of questions. So one is related to that. What do you expect, like a timeline around, when just like it happened for on the inference and training side, when do you expect some of these benchmarks to be made public or be standardized?
Yeah, pretty much under me just trying to champion it and like trying to get, one of the reasons I wanted to show up here is because I was like, oh, this community probably actually understands what workloads are, right, that need to be benchmarked. And I think, and so like there's no ongoing effort right now, but I'm trying to really find people who would actually be interested in this because, as much as I've been very deeply involved in points like MLPerf and so forth, they're all very quickly falling well behind what the state of the art, right? Like the automotive workload, they'll say, yes, we have a workload for benchmarking automotive use cases, but I'm like, that's still a single model. That is not what you talk to Cruise or NVIDIA and all those. They'll say like, that is not what I'm running. As like one of our speakers said, like I'm trying to run 40 different tasks at the same time with a real-time latency boundary constraint on them, which opens up this really rich space that I think we haven't touched on. So I think it's an opportunity for folks here to actually jump on and help build.
Cool. Any questions? Any other questions from?
Yeah, I have one question on this TinyML. Like, what would be the metric you think here that we should be like benchmarking here? Like, like a lot of them may be not compute bound, might be memory bound, might be quality bound. So like, what would be the good metric here?
It's ultimately energy, right? And so in that benchmark that I showed you, one of the things that we did was actually we built an energy benchmark because just the performance alone doesn't tell you the full story. So you have to have the energy component, right? At the end of the day, that's what matters.
Okay.
And most of it is just latency. Right? There's no throughput-oriented aspects. At least we haven't come across use cases that the industry is saying that, okay, well, there's some throughput-oriented use cases on embedded ML. We haven't seen that at all. But the biggest problem that we have seen is the need or the thirst for running multiple models and the splits that come about. So some of the talks, the two talks that I saw earlier were actually very, very relevant, but I have not seen any papers in the Tiny context.
Thanks.
Any more questions? So I see a question on the chat. So the question is, what are your thoughts on the need to go from inference to federated learning?
Yeah, this is an interesting one. I think a lot of people are very excited about federated learning, but I think it's actually really, really hard to realize in practice. And the reason is because it's easy to kind of think about federated learning on mobile devices and so forth, because you often don't worry about the comms aspect. Look at production use cases. You would ideally want federated learning because you're going to have all these small devices. But as I said, if you look at commercial use cases, it is 50% of the energy is literally just budgeted for comms. And 50% is budgeted for comms across this device having a 5-year lifespan, under the assumption that the comms is only happening maybe once a month. It's astounding how, just we know this, right? Communication is expensive. And so once you try and slap these two things together, right, which is I got a power constraint with a finite battery, and then I have federated learning, it does not look very exciting in production use cases. It actually looks like, well, we got this wrong. So this is why I like to say, I think our whole movement around the Internet of Things was a little misguided as a community. It's really, we have to kind of just convert it over to the intelligence on things. And the intelligence being maybe knowing when to communicate. It's not about just continuous connectivity, which is what the original IoT dream was. So yeah, I think the interesting aspect that's missing in research that I've seen is people haven't connected the fact that federated learning has to be thought about in the context of all these constraints you have. That's what I think is really sort of missing.
Makes sense. Thank you. Any other questions? I know we're a bit over time, so thanks, Vijay. Again, like as I said, if this was in person, again, probably would have been a resounding applause. But we really thank you for taking the time. And again, a lot of food for thought. I'm very happy that this talk has been recorded. So I think a lot of people will benefit from seeing it again and maybe ping you with more questions. So yeah. Thank you. So we're gonna end this keynote now and move on to the next session. And I think since we are running over, Yushin, do you think we're going to take a break, or do you want to dive right into the next session?
How about let's take a 2-minute break?
Yeah, let's take a 2-minute break.
Come back at 40.
40.
Yeah, thank you.
Okay, so we will resume at 40.
Okay, I think we should probably resume to our second paper session. Yeah, so welcome back, everyone. I know we have a really short break, but we're gonna start our second paper session in which we have 3 really exciting papers. And in these 3 papers, the general theme is focusing around how to enable multi-DN workloads sort of in a data center environment. So we're going to welcome the first paper, which is from KAIST. The paper is titled "A Heterogeneous Vector Array Architecture with Resource Scheduling for Multi-User or Multi-DN Workloads." The author and presenter is Yu Song-Hyo. So please feel free to start the presentation.
Hello everyone, I'm Sung-Hyun Yu from KAIST. Today, I'll be talking about a heterogeneous vector array architecture with resource scheduling for multi-user, multi-DNN workloads. This work is done with my colleague Jung-Hoon Kim and Professor Ju-Young Kim. This is the outline of my presentation. First, I will introduce motivation and limitation of previous AI accelerator system in data center. Second, I will describe the 3 key features of this work. Lastly, I will wrap up the presentation by showing the evaluation and experimental result, conclusion, and future work. Recently, multi-DNN machine learning workloads of multi-users are being performed in the data center. However, conventional hardware platforms do not fit into ML workloads. because in the case of CPU, it does not fit the tremendous amount of computation, and in the case of GPU, it is inefficient under certain condition and power efficiency problem, because GPU is designed for high throughput, so the performance and latency are not good in single batch requests. That's why AI hardware accelerator emerged for AI operations. Also, for supporting multi-DNN and multi-user requests, there should be a format that describes multi-DNN models. Open Neural Network Exchange Code ONNX is an open format to represent them. However, ONNX is not hardware friendly to be decoded in an accelerator and does not include user and request information. And there is the resource underutilization issue. The traditional AI accelerator use dedicated data paths for high throughput, but this inflexible hardware causes resource underutilization. Also, previous resource scheduling was only considered array processor computation overhead. To solve this limitation, we propose 3 key features. First feature is the unified model format that supports hardware-friendly decoding and multi-user, multi-request in AI accelerators. Second feature is a heterogeneous vector array architecture that supports multi-DNN workloads with flexibility. Last feature is heterogeneity-aware scheduling, which improves the underutilization problem with a heterogeneous vector array architecture. With these features, our work, heterogeneous vector array architecture, achieved 1.74 times faster and 14.4 more energy efficient than a comparable GPU. Now, let's move on to the 3 key features of this work. First of all, I will explain unified model format. UMF describes various MM models in an optimized packet format to enable fast decoding in hardware. This is how to convert MM model into UMF to run in an AI accelerator. First, we need to convert the model from frameworks such as PyTorch or TensorFlow into ONNX format. And then we can decode ONNX format and convert it into lightweight UMF, which is mapped to an AI accelerator. Continuing on UMF, I will talk about UMF structure. UMF is composed of a frame header, multiple information packet, and multiple data packets. The frame header includes the UMF, user, model, and request information. The information packet includes complete information to describe an operation node in the model. The data packet includes the actual parameter of each model layer. Each field of UMF is encoded in binary format to reduce the decoding overhead of model information in hardware. To give an example for UMF file generation, graph information and data of MobileNet version 2 from ONNX file are converted into information packet and data packet in UMF format. With UMF scheme, the size of graph information and data are reduced significantly by 73.3 and 75% respectively. For various DNN models, UMF effectively reduced the file size for model description by from 28 to 77%. From now on, I will explain our proposed architecture, which is called Heterogeneous Vector Array Architecture. In our proposed architecture, the multi-DNN and multi-user ML workloads can be processed with various scheduling algorithms. It consists of vector array cluster, short for VA cluster, that are main operational module, and load balancer that assign the request to each VA cluster. When the multi-user and multi-DNN UMF requests are incoming, the load balancer decodes them and stores the necessary model information to the request table. Using this information, the load balancer assigns these requests to the each VA cluster. Moving on the overall process flow, there are 3 steps. First step is that the load balancer assigns the multiple ML inference requests, and then these requests enter task queue in RISC-V scheduler of each VA cluster. Then, the RISC-V generates the layer or sub-layer level task from the request, and then it writes these tasks to scheduling table. Lastly, RISC-V scheduler assigns the task to available processor based on the scheduling table with the scheduling scheme. I will talk about computing processor design. We designed the n by n array processor and n-lane vector processor. They can complement each other to perform ML workload tasks with our flexible scheduling algorithm. The array processor performs the compute-intensive tasks like 3D convolution and matrix multiplication with weight stationary data flow. In the array processor, we try to increase the MAC utilization, so we use the double buffering and double registering. Also, the vector processor performs vector operation and the special operation like nonlinear activations. This vector processor complements the array processor by performing the array processor task. This scheme enabling flexible scheduling. In this slide, I'll be talking about scheduling algorithm. The scheduling algorithm decides how to allocate the task in the task queues to available resources in the VA cluster. We choose the round-robin scheduling as the baseline, which is one of the algorithms employed by process scheduler in computing. As this scheduling only focus on fairness, it could cause underutilization in the processors. So we propose the heterogeneity-aware scheduling algorithm. It selects the processor that complete the task earliest based on the execution time estimation for each task. Among the tasks, it selects the task that has the smallest idle time. As a result, it maximizes the utilization of heterogeneous resource by minimizing the idle time. Continuing on the characteristic of HAS, here is an example of scheduling scenario in a single VA cluster. The color of the box represents each request, and the number in the box represents the order of the task within the request. Gray box represents the idle time when the processor does not perform the computation. The above timetable shows the result when scheduling with round-robin scheduling, and the bottom timetable shows the result when scheduling with HAS. Round-robin algorithm choose the task from task queue in turn and assigned it to whichever can perform the task between the array processor or vector processor. On the other hand, HAS maximizes the utilization of heterogeneous resource by minimizing the idle time of each resource based on the execution time estimation. In consequence, in leverage heterogeneous performance behavior. If you look at the green box 2, red box 3, and green box 5, you can see the vector processor perform computation instead of being idle. Also, you look at green box 3 and green box 4, you can see the vector processor perform the task instead of array processor. It reduced the computational load of array processor and the total computation time. With this characteristic, HAS achieved better resource utilization and better computation time compared to round-robin scheduling. Next, I will present the evaluation and experimental result, conclusion, and future work. To evaluate the proposed heterogeneous architecture, we built a cycle-level simulator in Python. It is based on vector array processor performance models, which are cross-validated with RTL implementation. The simulator showed 99% accuracy in cycle count for major ML operations, including convolution, matrix multiplication, activation, and pooling. To emulate realistic ML workload in data center, we utilize 4 popular convolutional neural network models and 4 transformer models. Each model can generate a request with a certain probability in the time domain by varying the portion of CNN models from 0 to 100% with a step of 10%. We construct a total of 11 synthetic workloads. This slide shows experimental result of this work. For generated workload, we measured the total execution time and energy efficiency on 3 hardware options: GTX 1080 Ti GPU, the proposed HVA architecture with round-robin scheduling, and with HAS. The experimental results showed that the proposed heterogeneous architecture is promising for multi-DNN inference workloads. On average, HVA HAS is 1.7 times faster and 14.4 times more energy efficient than comparable GPU. HAS improved 41% performance from round-robin scheduling. One noticeable trend in the graph in that the latency reduction of HVA HAS gets bigger as the portion of CNN workloads increases. This is because the array processor with dedicated kernel mapping performs convolutional operation more efficiently than GPU's CUDA cores. On the other hand, the gain in transformer model involving many matrix operation is quite limited. It is because GPU is relatively well optimized to matrix operations. This is a cheap prototype of our proposed architecture. For verifying our work, the proposed architecture is fabricated in Samsung 28 nanometer CMOS process with 16 millimeter scale die area. The chip integrates single vector array cluster that has a RISC-V simulator, array processor, vector processor, and shared memories. And it operates at 0.9 volt to 1.1 volt. In conclusion, we present a heterogeneous architecture using array and vector processor for multi-user, multi-DNA inference workloads in data center. We propose unified model that support hardware-friendly decoding and multi-user, multi-request in AI accelerators. Next, we design heterogeneous vector array architecture that supports multi-DNA workloads with flexibility. We also propose a heterogeneity-aware scheduling that proposes the underutilization problem with a heterogeneous vector array architecture. Ultimately, the proposed architecture achieves 1.7 times higher performance and 14.4 times higher energy efficiency than a comparable GPU for a synthetic data center workload. As the initial experimental results showed that the proposed heterogeneous architecture was promising for multi-DNA inference workload, we have several future works to improve it. First, we plan to improve physical design of the array and vector processor. For example, the vector processor can have deeper pipeline with more custom instructions. Second, we plan to simulate the realistic application scenarios. Widening model to recommendation system, we consider to run the characterized ML inference workload used in Facebook data centers. Third, we propose better scheduling algorithm with different strategy and try to figure out which works well on what scenario. Lastly, we also plan to add a complete memory model to the simulator to measure the effectiveness of the proposed architecture well. This is end of my presentation. Thank you for listening.
Okay, thank you for the great presentation. So let me remind the attendees there is a Q&A section in Zoom, so feel free to ask questions there now or even later. So before we get any questions, maybe let me squeeze one question here. So you talk about the scheduling algorithm. So I'm wondering, have you tried different scheduling granularities between the models, and what do you think the impact might be?
Oh, when we schedule the task, I think the partition the task is way better scheduling, because the task is different. For example, the filter channel filter input channel is large, the computation time is large, and input channel is small, the computation time will be small. So I think it is need to partition the task into the small sub-layer subtask to they have the same computation time or the memory footprint.
I see. Yeah, thank you for the answer. And let's wrap up this one. And let's move on to the next paper. The next paper is titled Enabling Fast Deployment and Efficient Scheduling for Multi-Node and Multi-Tenant DNN Accelerator in the Cloud. And the paper will be presented by Su-Ling Chen. Feel free to take over and start the presentation.
Okay, thanks for the introduction. Hello everyone. My name is Su-Ling Chen. I'm a PhD student from Tsinghua University, and it's an honor to present our work on the ACS MD workshop today. My topic is enabling fast deployment and efficient scheduling for multi-node and multi-tenant DNN accelerators in the cloud. So currently, inference as a service is an important workload in the cloud. We have witnessed a rapid growth of deep neural network inference workloads in the data center, like Facebook and Amazon. And as we know, inference as a service workloads mainly run on the heterogeneous hardware platforms in the cloud, including GPU, FPGA, and ASIC. However, the service mode of most data centers is that one single user will monopolize a single physical node, leading to severe underutilization of hardware resource in the cloud. Thus, a basic technique to increase the hardware resource utilization in the data center is virtualization. And the most important feature of virtualization is to enable multi-tenancy sharing of the single node resources. Now, comes to the question about how to design a virtualized DNN accelerators. Let's review the history of GPU and DNN accelerators. So after the first GPU came out at 2000 year, it took 10 years for the first temporal multi-tenant GPU to come out, and then comes with first spatial multi-tenant GPU architecture. And we could find a similar trend on the DNN accelerators. Began from 2014, DNN accelerators were designed to achieve the best performance on the single task workload. It was not until the last year that the community began to explore the multi-tenancy of DNN accelerators. Similar to GPU, there came with multi-tenant DNN accelerators using temporal sharing at first. After that, our team was first proposed a spatial multi-tenant and multi-core-based DNN accelerators on FPGA. Then there were also spatial multi-tenant DNN accelerators proposed based on system array. So we could see that it brings up a new direction for the accelerators of designing spatial multi-tenant architecture. However, all this work only focused on the single node design. So today, I will introduce our work on realizing a multi-node, multi-core, and multi-tenant virtualized AI system. So the next question is, what ability do virtualized AI systems need? I think there should be at least two features that virtualized AI systems should support. The first one is scatter, that is multi-tenancy sharing to support multiple small networks like mobile net or ResNet. And the second one is gather, that is multi-node scaling out to run a single large network like GPT-3 or Transformer. So in addition to these two features, there is another important factor to consider in the cloud, that is performance isolation. Our previous study showed that failing to ensure performance isolation could result in serious performance deviation up to 50%. But how can we ensure the performance isolation of multi-tenant DNN accelerators? A simple answer is to ensure hardware resource isolation among multiple users, but there are still some challenges here. Taking Planaria as an example, we could see that hardware resource isolation is enabled naturally by spatial multi-tenant DNN architecture. The computing units and on-chip memory are easy to isolate. However, what about the off-chip memory bandwidth? We could see that there still exists confliction when multi-tenant sharing the off-chip memory bandwidth. So this is why the prior work is unable to achieve stable performance isolation for spatial multi-tenancy. So the first challenge here is how to achieve performance isolation and maximum performance at the same time. As shown in the left side, to enable scatter for multiple small DNN models, fixed bandwidth allocation is required for performance isolation. However, when it comes to support scatter for the single large DNN model, it requires dynamic bandwidth allocation for the optimal data flow to achieve the maximum performance. So to tackle this challenge, we set up a spatial multi-tenant hardware architecture with an FPGA-based prototype design. There are 16 virtualized cores and 4 computing groups. Each group contains 4 cores and 1 DDR bank. And groups are connected by a bidirectional NOC ring for on-chip data reuse. To enable hardware resource isolation on the off-chip memory bandwidth, we propose a multi-tenant isolated and runtime programmable off-chip bandwidth controller. So due to the time constraint, I won't dive into the details today, but will give you some key ideas of our proposed design. The first key idea is to support multiple bandwidth allocation using temporal threshold control on the XI burst package level for providing stable performance isolation. The second key idea is to use the instruction-driven runtime bandwidth management to achieve maximum performance for different data flow. Here we summarize the data flow into 4 types. The right side shows the first 2 types, including all forward no broadcast and all forward all broadcast. And here is the other 2 types of data flows. The 4 data flows can cover all the current multi-tenant architecture designs. Thus, our third idea is that by supporting the 4 data flows, our proposed off-chip memory bandwidth controller can be applied to all kinds of spatial multi-tenant DNN hardware architectures. In all, we propose a multi-tenant isolated and runtime programmable off-chip memory bandwidth controller to achieve both the performance isolation and maximum performance on the multi-tenant DNN accelerators at the same time. Next, let's take a look at the traditional process of compiler and scheduler to support multi-DNN workload in the cloud. At first, the input DNN models are processed by the compiler one by one during offline deployments. The compiler will traverse the search space to generate the performance lookup tables and instruction files with all the configurations considered. After that, the multi-DNN scheduler will take the performance lookup tables as input to manage the resource allocation during runtime, and the target instruction files will be loaded to the target core or node. Here, I will talk about the second challenge about large compilation overhead. As mentioned earlier, runtime scheduling requires accurate performance lookup tables to search for the best configuration. However, such performance lots are expensive, since the compiler needs to traverse the entire search space with all possible configurations. The problem is that the search space will grow exponentially from the single node to multi-node scaling out, resulting in a large and unacceptable compilation overhead, even for the offline deployments. Our evaluation shows that the compilation time for a 4-node cluster can be up to days or weeks, and the cost can be up to hundreds of thousands of dollars. Here are some detailed explanations about why the search space can be so large when scaling out to the multi-node system. Let's still take Planaria as an example. We can see from the right side that the compiler would generate a set of configuration tables for each DNN model. Inside each configuration table, the tails and subarray vision configurations for every layer of DNN models are all configurable. This makes the search space grow exponentially when supporting multi-node compilation. For example, Planaria will take nearly 6.5 thousand simulations for REST 950 on a single node cloud server. When compiling REST 101 on a 2-node cluster, this number quickly becomes 850,000. To tackle this challenge, we propose a multi-node optimized compiler and scheduler framework. On the compiler side, we decouple the compilation into 2 stages, that is static and dynamic stage. It is proposed in our previous work in FSM, and it can help to limit the search space without degrading performance. And it can generate the optimal instruction during runtime with million-second level overhead. For the scheduler side, we only generate the single node performance model during offline deployments. And then we build the accurate multi-node performance model using runtime updating. We show that a linear model with gradient descent optimization can build a simple but effective multi-node performance model, and it can greatly reduce offline deployment costs. Here shows the overview of our proposed multi-node AI virtualization system, 3M Visa. On the client machines, we use lightweight API remoting for remote accessing with negligible overhead. And the proposed compiler is employed for offline deployments. On the server machines, they are virtualized multi-core and multi-tenant DNN accelerator resource pools, and dynamic compiler for low overhead runtime recompilation. The central control node can support runtime resource scheduling of the multi-tenant, multi-node, and multi-core virtualized ISA-based DNN accelerators. Next, I will demonstrate some experimental results. We set up a 4 FPGA cluster with each FPGA with 16 virtualized DNN accelerator cores. The baseline designs are our prior work on FSM and Planaria. We set up a multi-DNN inference as service workload to evaluate the 3 matrices, that is system throughput, STP, fairness, and service level agreement, SLA. For the multi-node system performance on the multi-DN workload, when compared to the state-of-art solutions, our proposed system can improve the system throughput up to 6.5 times, achieve up to 39% higher SLA satisfaction rate, and up to 8.4 times better fairness. And as for the compilation overhead, the proposed multi-node compiler framework can achieve nearly 100 times faster for offline deployment, with 1 to 6 millisecond runtime recompilation overhead. For the runtime scheduling, the proposed schedule framework can achieve fast coverage during runtime with less than 10 scheduling run.
Sorry, Sui. We're a little bit running over time. Can we try to wrap up within 1 to 2 minutes? Thank you.
Okay, I will quickly jump into summary. So to sum up, Inference Accelerator brings a new direction for the accelerators in the cloud. We need multi-tenancy to support multiple small network and multi-node scaling out to support the single large network. The key challenge is to support multi-node scaling out for multi-tenancy are twofold. The first one is to ensure performance isolation and maximum performance at the same time. And the second one is that the compilation overhead can be very high even for offline deployments. So to tackle these two challenges, we propose a multi-tenant isolated and runtime programmable off-chip bandwidth controller and a two-stage compilation with runtime performance model updated. Okay, that's all. Thank you. Any questions?
Yeah, thank you a lot. Since we're a little bit running behind, please feel free to ask questions offline to the author. So let's move on to the last but definitely not least paper in this session. The paper is titled Multi-Tenancy, the next step in DNN acceleration. It's a paper from UCSD, going to be presented by Suresh Godrati. So please feel free to take over for the presentation.
Thank you so much for the introduction, Yushin. Hello, everyone. I'm Suresh Godrati from UC San Diego. Thanks for attending my talk today. I will talk about the significance. Today, I wanted to talk about the significance and importance of multi-tenancy as the next rising challenge and imminent next step in DNN acceleration. So with the ever-increasing demands for AI-based services, it has been projected that the total market cap for both cloud and edge solutions will significantly increase in the next few years. Due to the diminishing benefits from general-purpose processors, ASIC accelerators are becoming more prominent and more deployed for both cloud and edge solutions. To cope with these ever-expanding demands, one straightforward approach would be to constantly scale out resources. However, there are two major issues with this approach. There is a significant resource underutilization in cloud data centers, and also expanding the data centers with such a high rate will have devastating impacts on the climate due to the CO2 emission. To mitigate this serious underutilization, while pave the way towards green computing, supporting multi-tenancy where a single substrate is shared among multiple tenants is inevitable. However, multi-tenancy has not been the primary factor in designing DNN accelerators up to now due to the arms race for building the fastest DNN engine. As accelerators are increasingly becoming ubiquitous, research on multi-tenancy of accelerators is imperative. To this end, multi-tenancy enables this leap towards deployment of programmable accelerators in a cost-effective manner. Let's look at the history behind utilizing specialized computing systems and the role that multi-tenancy plays here. Here we are looking at GPUs as one of the most powerful acceleration fabrics and one of the most successful accelerators actually in the history of computing. So GPUs, they came out in 1999, and it was around 2001 that the first generation of general purpose graphic processors emerged. Due to the vast adoption of GPUs in the computing fabrics, supporting multi-tenancy in GPUs became the next challenge to enhance the resource utilization. And it was 2009 that the first practical GPU with support for multi-tenancy through temporal task allocation emerged. In 2012, the case for spatial task allocation in GPUs being motivated, and after that, there has been more than 150 papers that have explored multi-tenancy in the context of GPUs. With the huge advancements in AI algorithms and the slowdown of the trends in transistor scaling, communities started a shift towards developing specialized accelerators for the domain of machine learning in 2014. Since then, more than 1,000 papers have been published about designing machine learning accelerators. However, the actual resource utilization in the accelerators and their cost-effective adoption have not been the primary focus. Only in 2020, the community started looking into this matter, and there were two research works, namely PREMA and AIMT, that focused on multi-tenancy in DNN accelerators through temporal task allocation. However, temporal multi-tenancy does not fully tackle the issue of resource underutilization, as only one task is dispatched to the accelerator at any time. So in our recent work Planaria, which was published in Last Micro, we explored a different dimension for supporting multi-tenancy, which was a spatial task allocation and simultaneous execution of multiple DNN tasks, which I will briefly talk about this in this presentation. After these efforts in 2020, we have seen more papers paying attention to this aspect of DNN acceleration. For example, as Hyuk-Chun talked about, Herald in HPCA 21 was one of these great works, and which means that the community is paying more attention to this imminent need in DNN acceleration. So I will now give an overview and introduction to Planaria and discuss some of the design constraints and philosophies that we consider through developing this work, which they can be actually generalized and used in this realm. In this work, we propose the new concept of dynamic architecture fission in our Planaria accelerator that enables the underlying hardware to dynamically break into multiple smaller yet full-fledged logical DNN accelerators at runtime. This new capability by the hardware enables a spatial co-location of multiple DNN tasks and simultaneous multi-DNN execution. To do so, bringing for spatial multi-tenancy requires devising two main components. One is a microarchitecture with dynamic architecture fission capability, and second is a task scheduler that adaptively allocates resources to the dispatch tasks. Now let's look at some of the design objectives and constraints that we have. To design the microarchitecture for fission, we consider a set of objectives. First, we need to design a microarchitecture that is capable of creating standalone full-fledged logical accelerators. Second, we need to enrich the fission possibilities and accelerator reconfiguration schemes to serve various computational demands of DNNs. DNN graphs are usually very diverse with various computational characteristics such as data reuse, parallelism, and etc. Finally, the P array and on-chip buffer bandwidth utilization needs to be maximized. One important point here is that although we're talking about fission and breaking a DNN accelerator into smaller pieces, and usually when it comes to DNN accelerators, the main compute kernel is matrix multiplication, and mostly we talk about the compute resources, but we can't just take a scissor to cut the accelerator into smaller pieces. The on-chip memory management and utilization is actually a key factor here. While considering these objectives, there are also two design constraints that need to be taken into account. One is architecture fission should impose minimal power and area overhead to the hardware. Otherwise, we would defeat our purpose. And second, the baseline frequency should not be reduced. So to strike a right balance between the flexibility and the overhead of the design, we propose a microarchitectural blocks called Fission Pod as the heart of the Planaria accelerator. So in Fission Pod, actually Fission Pod interweaves the compute and on-chip memory to provide a balanced cooperation of them while minimizing the cost of fission. In this unit, a group of P subarrays are co-located and a partition memory substrate is shared amongst them. Now, let's see how the architecture of this unit provides the aforementioned objectives while also considering the constraints. As one of the key features in this block, we introduced omnidirectional systolic subarrays that enables moving data in all four directions between the Ps, which leads to providing more variegated logical subarrays that could be suitable for some DNN layers. To facilitate the omnidirectional flow of data, not only within subarrays, but also across the configured logical accelerators, Fission Pod harbors a set of bidirectional ring buses that move the input activations and partial sums across various P subarrays in all directions. With this omnidirectional movement, now it's possible to construct, for example, fat and short or tall and thin logical arrays to either benefit more from input data reuse or partial sum data reuse. These buses can be also turned off if there is no communication between the adjacent P subarrays based on the target fission configuration, for example, for a case that the DNN layer enjoys more coarse-grained parallelism. This intra and intra-omnidirectional flow of the data paves the way to enrich these fission possibilities. Each PE subarray is also coupled with a small segment of a SIMD vector unit to enable creating standalone and full-fledged logical accelerators, because it's not just a matter of convolution or gem layers. We need to think about other layers such as activation, pooling, and etc. Based on this fission configuration, if a number of subarrays are stacked vertically, these SIMD vector units, they can be bypassed. Additionally, the shared memory substrate in the fission pod is connected to the PE subarrays by read and write crossbars to provide the flexibility required by various patterns of communication in fission scenarios and maximize the utilization of the PE arrays and on-chip buffer. Moreover, since this memory substrate is shared amongst a group of subarrays, not all of them, the required flexibility in the communication patterns can be provided by using low-cost or low-radix crossbars, which basically minimizes the overhead of fission. Now let's look at the overall architecture. We integrate a collection of fission pods and expand the bidirectional ring buses across the whole design to increase the number of fission possibilities. Note that all these ring buses are pipelined to eliminate any critical path. This is possible due to the natural behavior of systolic architectures. In this work, we're looking at systolic architectures, and usually in systolic arrays, there is a wavefronts of data that's being pumped to the compute resources. So pipelining was actually possible here. We implemented and evaluated an instance of the Planaria with 4 fission pods and 16 number of total subarrays. With this design, Planaria supports simultaneous execution of up to 16 DNNs and provides 65 fission scenarios in total. For example, even if you allocate 16 subarrays to a DNN, you can configure them in different formats. That's how the number of fission scenarios is about 65. So in efficient scenarios, multiple fission pods can be potentially composed together, or a logical accelerator can take a portion of fission pod while the other portion can be composed with other pods. As the second prerequisite for spatial multi-tenancy, we also defined a task scheduling algorithm. So to fully leverage dynamic architecture fission while maximizing the throughput, fairness, and quality of service, we developed a task scheduler with following characteristics. It's aware of the optimal fission configurations for various layers of DNNs to maximize the utilization and efficiency. So to do so, we did an offline profiling step to search over all possible fission scenarios and find the optimal configuration for each DNN layer, given a number of available subarrays, and generate a set of performance tables to be used during scheduling. Second, it is also quality of service aware to leverage the intrinsic slack time available in tasks, quality of service constraints during co-location to maximize throughput, while adhering to service level agreements. And finally, it allows the reallocation of the tasks to minimize checkpointing overheads. So we compared that proposed design to Prema that was a recent effort that enables multi-tenancy through temporal task co-location. So as you can see, Planaria with spatial task co-location could provide significant improvements in throughput, SLA satisfaction rate, fairness, and in various workload scenarios, and quality of service constraints. Now let's look at some of the lessons that we could learn from this spatial multi-tenant design and discuss them. So one key important factor is that if you look at actual P resource utilization for various workloads, while running them on a conventional systolic array, which is a monolithic big array, and compared to Planaria, which has this notion of reconfigurability and adapting to the computational needs, we can see that resource utilization, P resource utilization, it could be really low in a conventional systolic array. It's about 20% on average, while Planaria and its adaptation to the requirements of the DNNs can improve the resource utilization to about 70%. What we can see here is that supporting multi-tenancy through time multiplexing cannot sufficiently utilize accelerator resources, because at one time, only one DNN is mapped to the hardware. So even if the DNN graph is not a great fit for a for an array, then there's going to be a lot of resource underutilization. So then I wanted to kind of point out the notion of reconfigurability and its importance to adapting to the needs of DNNs to increase their resource utilization. Also, one more important thing is that now, even if there is still resource underutilization, although we adapt to the needs of DNN, the remaining resources can be reclaimed and utilized through architecture fission to co-locate multiple DNNs. The second lesson is actually the need for flexible architecture fission. So here is the table that considers the 15 most used fission configurations in different DNNs. It's a really complex table. What the point is here is that, as you can see, all these 15 most prevalent use case for fission configurations, they were used by different DNN layers. And for example, as you can see, the black case, which actually it's like a thin and tall systolic case, was used for all the DNN benchmarks that we had. And that was only possible with this kind of reconfigurability notion in the hardware. So again, I wanted to come back to the reconfigurability feature, which it's necessary to adapt to the needs of the DNNs. And as you can see, the hardware enabled these various fission configurations and architectures in heterogeneous mode to adapt to the needs of DNNs. So this is just the tip of the iceberg. So there are a lot of kind of follow-on works could be done in this area. And I'm really happy that this workshop was kind of coordinated today, which actually provided this opportunity for people to talk about this type of the designs. I think there are a lot of future research work that can be done here. Definitely security support for isolation in multi-tenant DNN accelerators is the next challenge. When we talk about multi-tenancy, always the next thing is, okay, how do we want to provide security support and isolation? We can look into, so our works, we did it in a inference as a service data center scenario, but definitely there are advanced edge applications such as AR, VR, autonomous driving that they benefit from multi-tenant and multi-DNN acceleration, compiler optimization, and operating system support that can be explored. We can look into emerging workloads such as recommender systems that they actually have a different type of computation characteristics. They are more memory bound, so how it can actually multi-tenancy be enabled for them. And even architecture fission by its own can be also explored for sparsity and sparse DNN acceleration. So to engage the community more and provide some tools and mechanisms to explore these concepts, we open sourced our simulator for Planaria, which includes the hardware simulator and the task scheduling mechanism and algorithm. So we have open sourced it, and I hope that could be useful for future research. Now, I would love to take any questions, if there is.
Yeah, thank you, Suresh, for the very insightful talk. But unfortunately, due to time constraint, we'll have to move the Q&A offline. So please feel free to ask questions offline.
Sure.
Before
Thank you so much.
Before we wrap up, please give all the presenters in this session a round of virtual claps. They're all really great presentations. So I think that wraps up this paper session. For the next session, we're going to move on to the second keynote, which will give to Liangzhen for the moderation.
Peter, are you there? Oh, I think you're on mute.
Okay, can you hear me and see the slides?
Okay, yeah, we can see it. Okay, thanks. It's my great pleasure to introduce our second keynote speaker, Peter Rouhani. So Peter is a principal research manager at Microsoft Azure Cloud Accelerated Systems and Technologies. Peter received her PhD degree in computer engineering from the University of California, San Diego. Her research interests includes algorithms, hardware, and software for design for succinct and assured deep learning. Peter has co-authored more than 40 major patents and publications. Her work has been published at top-tier machine learning, computer architecture, and security venues, including RIPS, ISCA, SPROS, ISLPED, DAC, ICCAD, FPGA, FCCM, SIGMatrix, and SMP magazines. So without further ado, take it from here.
Thank you for the introduction. I try to keep the keynote short and sweet. So perhaps to this audience, it doesn't even need an introduction to say deep learning is AI, and in particular, deep learning is providing a paradigm shift in our ability to comprehend raw data. And it's already been adopted in order to improve the quality of service in applications that we use on a daily basis across various domains, such as language modeling, web search, computer vision, speech recognition, and so on and so forth. Besides the conventional applications of AI that we've used on a daily basis, AI is also finding its way in new applications such as healthcare and also sustainable farming, with the hope that it can help improve the quality and the quantity of, for instance, the food that can be produced. One of the recent technological applications of AI that's powered by GPT-3 models is a GitHub Copilot. If you haven't checked it out yet, I highly encourage you to check out the paper, the OpenAI paper, and also the GitHub Copilot blog on the topic. Essentially, what this tool does is you can describe the task and what you're trying to accomplish in natural language. And the tool outputs some sample codes for you in order, and depending on also what syntax you want to use, what language you want to use, it generates some samples for you that you can essentially adopt or just reject them. It's not cracking some of the coding interviews just yet, but you'd be amazed by the quality of the output that these models generate. And also just the idea and the potential that AI can have in the future of coding, and a lot of new applications that we might not be aware about today. Now that we touch the surface and the importance of AI and the role it can play in our daily life, let's take a few minutes in order to look into the AI trends, particularly through the lens of compute, and also discuss some of the high-level requirements that an AI computing platform should have in order to be scalable and useful for different AI workloads. So in this figure here, I'm listing some a subset of popular AI models as a function of model size, or in other words, the number of parameters each of these models has over the course of past 10 years. In just last 3 years, we've observed more or less 3 orders of magnitude increase in the size of these models. The problem is that even if you pick each of these workloads and the applications that are deployed based on these models, each of them have their own unique requirements. For instance, the length of the sequence length, or the length of the prompt that is used to query, let's pick one of these generative models, say GPTs, Turing, NLG, Megatron, determines, for instance, whether these particular workloads lies in the compute bound region or memory bound region. And for some workloads, you even have in one phase you are compute bound, and in the other you are memory bound. Same story goes to for instance, mixture of expert models. Even though they provide a nice trade-off between compute and memory, particularly during training, they introduce their own set of challenges during inference, particularly around resource utilization and batching. The details of these workloads is out of the scope of this talk. What I want you to take away from this slide, though, is AI is and a fast-paced growth, and there is no sign of a slowdown. And B, there is no one solution that fits all workloads. Now that we talk about the scale of the problems we are dealing with, and have a high-level understanding that each of these workloads have their own unique requirements, let's talk about the model topology. Since 2012 and the emergence of AlexNet, CNN models or convolutional neural networks became the go-to architecture for computer vision, and long short-term memories or LSTMs were the popular architecture for speech recognition and text analysis. With the emergence of transformers, now these days we see that like transformer and its variants like are the mainstream topology being used in various domains, including vision, including natural language processing and speech recognition. That said, that doesn't mean that like transformer is the solution for all workloads. There are a tail of workloads that still require DNNs, that still require LSTMs, or even like the efficient version of the transformers like that are like developed based on neural architecture search or like are customized for specific applications, have operations in them that is common, for instance, with CNNs and LSTM. As such, it's really important when you are designing an AI computing platform in order to be sure that you can support different operations and you have the flexibility in order to support a new operation as they come along, because we don't know like what the future holds for us. And just a few years back, there was no sign of transformers, and now they are the mainstream topology. So if I want to summarize like the features, the high level like qualities that we need to look for, at least at a very high level, when we are designing an AI computing platform based on the requirements, these AI platforms should be scalable, meaning that like you should be able to support various scale size models in a cost efficient and sustainable manner. It should be future proof because like there is always chance that there would be a shift in terms of the operations needed for AI models, and the different workflows have different requirements. It should be generalizable, meaning that it should we should be able to like serve different family of models and not just over-engineer the design for one particular benchmark or one particular application. And last but not least, it should be flexible, meaning that like it should allow for algorithmic innovations along different dimensions such as data type, sparsity, conditional compute, and so on and so forth, that I'm going to spend more time toward the end of the talk on. We designed Project Brainwave with the aforementioned like features in mind. Project Brainwave and its customized neural processing units enable us to have a flexible, ultra low latency and cost solution for different workloads. Project Brainwave has been used in larger scale production since 2017 and is now serving millions of users by empowering like different web search and also like image processing and question answering services across Microsoft. With that said, let's take a look into the Project Brainwave and its infrastructure. When we are designing an AI computing platform, like the fabric that you use is like the first choice in a sense. And there is a trade-off between flexibility and efficiency. There are essentially two types of neural processing units or NPUs out there at a very high level. One is like kind of like a hard NPU, and the other like soft NPU. With hard NPUs, you need to commit to a set of like design choices at the design time, meaning that like, for instance, what data type you want to use, what operations you want to optimize for, what's your balance between like the compute and memory. You have some of those constraints with soft NPU as well, but it gives you more flexibility and makes your design a little bit more future-proof and gives you more flexibility in order to innovate and adjust based on the requirements of the new workloads. At Microsoft, we use like different solutions, CPU, GPU, soft NPU, and hard NPUs to essentially satisfy the requirements of our different workloads. Today, I just want to talk about the soft NPU project, and in particular, Project Brainwave. So the journey started back in 2011 with the launch of Project Catapults to investigate the power of using FPGA at cloud scale. By 2017, over 1 million servers were with FPGAs were deployed at hyperscale. Even though Project Catapult was not designed initially with AI workloads in mind, thanks to the efficiency of our infrastructure and also the configurability of FPGAs, we were able to repurpose those hardwares and use it for AI workloads. And now today, like over 50 major production scale models, like for different workloads, is being served on Project Brainwave. So how this efficient infrastructure looks like? At the outer layer or on the edge, we have the CPU compute layers. At the center, we have the conversion network at the data center scale, and we have FPGAs or configurable fabric sitting in between the two. One of the key features of Project Brainwave is the concept of scalable hardware microsystems. Even though these FPGAs are uniformly distributed and also co-joined at the hip with the CPU, they can, physically, they can logically be disaggregated and pulled together in order to form a hardware microservice. Why does it matter? It's because it enables us to scale up efficiently and also pull together and aggregate the on-chip and also the compute resources of different FPGA hardware in order to meet the requirement for different workloads. But if you need more memory, for instance, we can pull in more nodes. If you need more compute, we can do so. And this way we can customize the underlying platform in order to adjust it based on the requirements of the hardware. I'm not going to talk about the details of the architecture of either Project Catapult or Brainwave here, but I refer you to a lot of publications and also blog posts around the architectural details if you are interested. One thing I do want to emphasize on though is the flexibility features that reconfigurable FPGAs enable us to use. And in particular, I want to talk about a customized data type named Microsoft Floating Point that we leverage on Project Brainwave in order to get better latency in order to reduce the cost and also while keeping up the accuracy of the model. So if we take a step back and look into the details of the AI models, one key part of the current AI models is dense matrix multiplication. And typically you need to do millions of these operations for each query that comes along. And if you want to do it with high bit widths, the cost just is unimaginable. So with that in mind, we designed a custom data type for AI workloads that's co-designed with the architecture of Project Brainwave, and we call it Microsoft Floating Point. Here I'm showing you on the right, the accuracy of ResNet 50 ImageNet benchmark for different bit widths. And the area, the normalized MAC area cost corresponding to that different data specific bit widths. As you can see, variants of MSFP data type together as you change the number of mantissa bits can form a new Pareto frontier for computational performance compared to conventional data types, quantized data types such as int8, before16, and int4. The key here is that you need to keep the accuracy of the model up as you quantize the model. So for fixed accuracy, you want to have much better area overhead and energy consumption. We tested the MSFP data type. As I said, one of the key features that for any changes that you introduce is that it needs to be generalizable. With that in mind, we tested MSFP data type across different first-party and third-party workloads. Here I'm listing like different like CNN, transformers, and RNN models that we looked into in order to see the impact of quantization on the accuracy. So it's a pretty dense table, but on the second column, I'm showing the full 32 accuracy as the baseline, and everything, all the other accuracies are normalized compared to this baseline. The third column corresponds to MSFP16, and MSFP16 data, when we quantize the model with this data type, we didn't even need fine tuning. This is unlike, like for instance, int8 quantization, that usually you need some quantization ever fine tuning, or you need to play some tricks like doing clipping and like adjusting the batch norm and so on and so forth. But with MSFP16, we don't, it just works outside of the box, and it doesn't need like any fine tuning across like different workloads that we'll look into. And like for CNNs, we also look into some very dense models that are supposed to be hard for quantization, as well as conventional models like ResNet50, VGG, and so on. And then like in the rest of the columns, you can see the accuracy, the normalized accuracy for different bit widths. What I want to highlight here is that like MSFP12 data type, which is more efficient than like int4, has a very good accuracy, particularly for larger scale models such as BERT models. I can recover greater than 99% accuracy of the baseline. And in the last two rows, I'm highlighting the efficiency, the memory efficiency, and also arithmetic density improvement that can be achieved by different bit widths compared to the full 32 version. To give you a highlight of what we discussed so far is a Project Brainwave is deployed at production scale, and the MSFP data type is tested on more than 50 like first party workloads, as well as like different open source and pressure tested like in order to make sure it's generalizable and it works across various generation of models. MSFP16 data type, as I mentioned, like doesn't require any quantization, ever fine tuning, but when you convert like a pre-trained model and quantize that, and it has 3x lower cost compared to B416, and MSFP 12 achieves 4x lower cost compared to int8 while having competitive accuracy. With that said, I want to wrap up the talk by highlighting some of the gaps between the current AI paradigm versus human neocortex and biology, and highlight the fact that even though we came a long way in order to make AI more scalable, more efficient, we are far, far away from being as efficient as human brain. And there is a lot of headroom for improvement. So I really hope nobody is surprised in the audience that when I say like there is a huge efficiency gap. In fact, like orders of magnitude gap between human neocortex and current deep learning. What I want to highlight today is the gap along like 5 different categories: computational efficiency, sample efficiency, generalization, adaptability, and reasoning. So just in terms of the computational efficiency, we know that like the current approach for training these neural networks and also inferencing them is not necessarily the most optimized in terms of the power and compute. Works along quantization, sparsity, conditional computes are helping to reduce the computational efficiency, but there is like around like 8 orders of magnitude gap still until we close to reach the efficiency of the human brain. One other thing is sample efficiency, particularly around training. Like humans are really efficient in terms of if they see one sample, next time when they see it, they know what that is. But for artificial intelligence, and at least as of today, large data set is needed in order to train these models. Even though with like larger scale models that we are dealing with today, there is less requirement to repeat one sample over and over. there is like a requirement to include more samples in order to avoid overfitting and like also like get the most out of the model. As a matter of fact, like there's a rule of thumb, for instance, that like if you scale up your model by size of 8, you need to scale up your data set by size of 5 in order to get the best efficiency of your model, and so on and so forth. This goes also for generalizability. Like as humans, we can generalize concepts out of the scope of the samples that we already observe, but extrapolation is kind of hard for AI today, and this makes it harder and harder in order to, for instance, like pre-train a model and use it in different downstream applications. Even though we are seeing like a lot of improvement in pre-training models and transfer learning, there is still headroom for improvements in order to get best results in zero-shot settings in downstream tasks that we didn't have a representation from in our data set initially. Adaptability is another one. As humans, we always like continue to learn, and also like it's not like a one-time process. We train something and then.
Hi, Beta. Sorry to interrupt. Just to kind of remind, like if you can wrap up in a couple of minutes, that will be great.
I have 2 more slides. I'm ready.
Okay, perfect. Thank you.
Of course. Yeah, and reasoning is like the last thing that I wanted to highlight here in terms of like different capabilities that AI should have, and also we should be able to explain the output that we get. That said, I think we are all in agreement that like the dense float matrix arithmetic is kind of solved, and AI is fast evolving with no sign of a slowdown. The upcoming wave of algorithmic innovations, I believe, is rooted in a true co-design of algorithms, software, and hardware. And if you are interested to work on that challenge, we are hiring at all levels for data scientists, AI researchers, computer architects, system and networking, and send me an email if you are on the market.
Thanks. Thanks, Peter, for this great keynote talk here. Thanks again. And I think we are kind of running out of time for the closing remarks. So I just want to thank our speakers and thanks all attendees again for joining this workshop. And with that, that kind of concludes this workshop. And thanks very much for everyone for joining and participating in this workshop.
Yeah, thanks again to all the speakers, and thank you to the organizers. And yeah, we'll hopefully, like, the videos will be available online, so more people can watch it later as well. Thank you.
Thank you for the great workshop. Thank you so much.
For those that are interested, right after in this same track, we will run the AI security tutorial.